Our universe might be a grand illusion. We are about to explore 50 of the most bizarre theories in space and cosmology, ideas that will stretch your imagination to its absolute limit. By the end of this journey, you will see reality itself in a completely new light. We will ask if our cosmos is a computer simulation, and if the flow of time is just a convincing trick. This is a deep dive into concepts that challenge everything from the birth of the universe to the ultimate fate of consciousness. Are you ready to question the foundations of your existence? The very first theory on our list is one that has moved from science fiction into serious scientific debate. It is the simulation hypothesis. The core idea is staggering. Our universe, with all its galaxies, stars, planets, and you, might not be a fundamental reality. Instead, it could be an incredibly advanced computer simulation, a cosmic video game running on the hardware of a civilization far more advanced than our own. Philosopher Nick Bostrom formalized this argument, suggesting that if any civilization ever reaches a stage where it can run vast, realistic simulations of its ancestors, then the number of simulated beings would vastly outnumber the real ones. Statistically, you are more likely to be a simulated mind than a biological one. This is not just a philosophical thought experiment. Some physicists point to potential evidence within the fabric of reality itself. They note that at the tiniest possible scale, the Planck scale, spacetime appears to be pixelated, not smooth. This fundamental graininess could be interpreted as the resolution limit of the simulation, the underlying code of our universe. And then there are the glitches, unexplained quantum effects, particles that seem to know they are being observed, or cosmic constants that appear perfectly fine-tuned for life. Could these be the equivalent of software bugs or even intentional Easter eggs left by the programmers? This theory forces a profound question. If our reality is a simulation, what lies outside it? And what is the purpose of the experiment we are all a part of? This pixelated nature of reality leads us directly to our second bizarre theory. If our universe is not a simulation, perhaps it is something even stranger, a hologram. The holographic universe principle is not a metaphor. It is a serious proposal in theoretical physics, suggesting that all the information that makes up our three-dimensional world, every star, every mountain, and every thought in your mind, is actually encoded on a two-dimensional surface at the edge of the cosmos. We are living inside a projection, a cosmic illusion of depth, much like a hologram on your credit card appears three-dimensional but is etched on a flat, two-dimensional surface. The roots of this idea come from the mysterious physics of black holes. Physicists like Leonard Susskind and Gerard T. Hooft were grappling with a paradox. When something falls into a black hole, what happens to the information it contained? The laws of quantum mechanics say information can never be destroyed, but black holes seem to erase it completely. Their groundbreaking work suggested the information is not lost inside. Instead, it is smeared and preserved on the black hole's two-dimensional event horizon, the point of no return. Think of it like taking a complex three-dimensional sculpture and carefully flattening it into a perfect, detailed painting. All the information is still there, just stored in a different form. The holographic principle takes this black hole logic and applies it to the entire universe. Our entire cosmos, in this view, could be the holographic projection from information stored on a distant, two-dimensional boundary we cannot see. Your experience of moving through a solid, spacious world is an incredibly convincing illusion generated by this underlying code. This means the true nature of reality might not be in the three dimensions we perceive, but on a vast, flat cosmic canvas at the edge of everything. It suggests that the fundamental building blocks of existence are not particles or strings, but bits of information. We are not just made of matter, we are made of data. If the universe is truly a hologram, then our consciousness itself is part of that projection. But what if your consciousness is the only thing that is real? This leads us to one of the most unsettling thought experiments in all of physics, the Boltzmann brain paradox. Named for the physicist Ludwig Boltzmann, this idea emerges from the deep laws of thermodynamics and probability. In a universe that tends toward chaos and disorder, how did we end up in such an incredibly ordered state? Statistically, the most likely outcome is a featureless soup of particles, not a cosmos with galaxies and life. The paradox suggests that in an infinite or nearly infinite universe, random particle fluctuations will eventually create any possible configuration of matter, no matter how improbable. Given enough time, the random jostling of atoms could spontaneously assemble a fully formed, self-aware brain, complete with all the memories and sensory experiences of a lifetime floating alone in the void. This brain would believe it is a person living in a real world, but its entire reality would be a fleeting accident. The terrifying implication is this. In an eternal, chaotic cosmos, it is mathematically more probable for a single, isolated consciousness to pop into existence with a false memory of an ordered universe than for an entire 13.8 billion-year-old cosmos like ours to evolve naturally. You could be that brain right now, experiencing this very moment as a brief, random glitch in an endless sea of nothingness. Cosmologists grapple with this paradox because it challenges our most fundamental assumptions about reality and observation. If our universe is the result of a rare, low-entropy beginning, why is it so perfectly ordered for life? Or are we simply the unlikely fluctuation that happens to be aware of itself? The Boltzmann brain forces us to confront the eerie possibility that the past, the world around us, and even the laws of physics might be nothing more than an elaborate, temporary illusion manufactured by a solitary mind that just blinked into being. Escaping the lonely void of a Boltzmann brain requires a path out, a cosmic tunnel through the very fabric of reality itself. This brings us to the twisted siblings of the black hole, and a theoretical passageway that could make interstellar travel possible. We are talking about white holes and wormholes. If a black hole is a cosmic drain from which nothing, not even light, can escape, then a white hole is its theoretical opposite. It is a region of spacetime that only expels matter and energy. Nothing can ever enter a white hole from the outside. It is a one-way exit door for the universe, a fountain of creation constantly spewing out light and particles. While black holes are predicted by Einstein's equations and we have observed their effects, white holes remain purely mathematical possibilities. Some theories suggest they could be the other end of a black hole, a connection point in the fabric of spacetime where everything a black hole swallows is violently ejected somewhere else, or perhaps into another universe entirely. This idea of a connection leads directly to one of the most tantalizing concepts in all of physics, the wormhole. Also known as an Einstein-Rosen bridge, a wormhole is a theoretical shortcut through the folded layers of spacetime. Picture the universe as a vast sheet of paper. To get from a dot on one side to a dot on the other, you would normally travel the long distance across the entire page. But if you could fold the paper so the two dots touch, and then pierce a tunnel directly through that point, your journey becomes instantaneous. A wormhole is that tunnel, a bridge connecting two distant points in space, or even two different points in time. This is the stuff of legendary science fiction, from Interstellar to Star Trek, offering a solution to the immense, lonely distances between stars. The problem, however, is stability. According to our current understanding, any naturally occurring wormhole would be unimaginably tiny, existing at the quantum scale, and it would snap shut in an instant. To hold a wormhole open wide enough for anything to pass through, you would need a form of matter with truly bizarre properties, something physicists call exotic matter. This is not just unusual matter. Exotic matter would need to possess negative energy or negative mass, meaning it would gravitationally repel normal matter instead of attracting it. This repulsive force could, in theory, prop open the throat of a wormhole, preventing its collapse. The catch is, we have never observed such a substance. It exists only as a speculative solution in the equations of general relativity. So while wormholes offer a breathtaking vision of cosmic travel, they remain locked behind a door for which we have not yet found, or perhaps cannot even create, the key. They are a beautiful promise written in the language of mathematics, waiting for a reality that might one day catch up to the dream. The dream of a stable wormhole hinges on exotic matter with impossible properties. Yet the quantum world is already filled with impossibilities that defy our everyday logic. This brings us to a theory that doesn't just propose one hidden tunnel, but an infinite number of branching realities. We are entering the many worlds interpretation of quantum mechanics. For decades, the dominant view was the Copenhagen interpretation. It stated that a particle, like an electron, exists in a haze of all possible states, a superposition, until it is observed or measured. At that moment, the wave function collapses and the particle picks a single, definite reality. It is as if the universe cannot make up its mind until we look at it. This always raised a deep philosophical question. What or who does the observing, and why is consciousness seemingly so special? In the 1950s, a young physicist named Hugh Everett proposed a radical and elegant alternative. He suggested the wave function never collapses. Instead, every single possible outcome of every single quantum event actually happens. The universe literally splits or branches to accommodate each possibility. In this view, reality is not a single thread but a constantly forking, ever-growing tree of parallel worlds. Take the famous thought experiment of Schrödinger's cat. A cat is placed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and releases the poison. According to quantum rules, until you open the box, the atom is in a superposition of both decayed and not decayed. The Copenhagen interpretation says the cat is both alive and dead in a ghostly state until observation forces a choice. The many worlds interpretation offers a different and perhaps less cruel resolution. At the moment the quantum event occurs, the universe splits. In one branch, the atom decayed, the poison was released, and the cat died. In the other, perfectly real branch, the atom did not decay, and the cat lives on, purring in its box. Both outcomes are equally real, but they play out in separate, non-communicating universes. The implications of this are utterly staggering. Every choice, every random quantum fluctuation in a star or in your brain creates new branches. There is a universe where you took a different job, a universe where dinosaurs never went extinct, a universe where every possible variation of history unfolds simultaneously. Your identity is not a single self, but a vast, branching tree of selves, each living out a different destiny in a different world. This solves the observer problem neatly. There is no special collapse because every outcome occurs somewhere. The version of you in this branch simply experiences one specific outcome, unaware of the other yous in the other branches. The many worlds theory is not science fiction. It is a mathematically consistent and, to many physicists, a simpler interpretation of quantum mechanics than the Copenhagen view. It removes the need for a mysterious collapse, yet it replaces that mystery with a cosmos of unimaginable plurality, where every possibility is not just imagined, but is being lived out in a reality just as solid as our own. It suggests that somewhere in the vast fractal of existence, every story ends and every story also begins again. The idea of infinite branching realities is a dizzying one, but it still begins with a single point of origin, our own Big Bang. What if that explosive beginning was not a unique event, but the echo of a death in another cosmos? This is the startling premise of black hole cosmology, a theory suggesting our entire universe was born from the interior of a collapsing black hole in a parent universe. We are not the first chapter of existence, but a new volume written from the ashes of a stellar giant. The standard Big Bang model presents a fundamental problem. It describes the universe exploding from a point of infinite density and temperature, a singularity where the laws of physics as we know them completely break down. Science cannot peer beyond this veil, but what if that singularity was not a mysterious beginning, but a known physical phenomenon? A black hole's core is also a singularity, a point where matter is crushed out of existence. Black hole cosmology proposes a breathtaking connection. When a massive star collapses in a far-off universe forming a black hole, the incredible forces at its heart might not lead to a dead end. Instead, the singularity could act as a cosmic seed, triggering a new Big Bang and birthing an entirely new spacetime continuum, a baby universe with its own laws and constants, hidden forever behind the event horizon of its parent. In this view, every black hole is not a tomb but a womb. Our cosmos, with all its hundreds of billions of galaxies, could be the interior of one such black hole existing in a much larger, older universe. This elegantly explains the initial singularity of our Big Bang. It was simply the core of that progenitor black hole. This theory, sometimes called the fecund universe theory, paints a picture of a grand, self-replicating multiverse. Universes beget new universes through their black holes, creating an eternal, branching tree of cosmic lineages. Our universe's own black holes could be spawning countless other universes right now, each forever separate from our own, each with its own unique physics. Some versions of this idea suggest these child universes might inherit but slightly alter the fundamental constants of their parent. This provides a compelling mechanism for cosmic evolution. Universes that produce many black holes and thus many offspring become more common in the multiverse. If certain physical constants, like the strength of gravity or the mass of an electron, are favorable for forming stars and black holes, those constants would be naturally selected for across generations of universes. Our own universe, perfectly tuned for the creation of stars that eventually collapse into black holes, might be a product of this grand Darwinian process playing out on a cosmic scale. We exist in a universe that is good at making more universes. This transforms our place in the cosmos. We are not just inhabitants of a random explosion. We are living inside a link in an unimaginably vast chain of creation, where the death of a star in another reality was the very breath that gave life to everything we know. If universes can be born from black holes, then perhaps we can detect the presence of another cosmos tugging on our own. This is not mere speculation, but a startling observation that defies our understanding of cosmic expansion. In 2008, a team of scientists led by Alexander Kashlinsky made a discovery that sent shockwaves through cosmology. They were studying the motion of massive galaxy clusters by analyzing the cosmic microwave background, the faint afterglow of the Big Bang. According to the standard model, the universe's expansion should cause these clusters to move in random, chaotic directions, like leaves scattered by a gentle wind. But that is not what they found. Instead, they detected a mysterious, coherent stream. Hundreds of galaxy clusters spanning billions of light years were all moving in the same direction at a staggering speed of over 2 million miles per hour. This colossal, coordinated motion was dubbed the dark flow. It was as if some immense, unseen force was pulling a significant portion of the observable universe toward a specific point beyond the cosmic horizon, the edge of what we can possibly see. The gravitational pull required to cause this flow would have to be unimaginably vast, far greater than anything our universe's known matter and energy could produce. So what could possibly be exerting such a titanic tug? The most radical and perhaps the only plausible explanation is that the dark flow is evidence of a multiverse. The theory suggests that our universe is not floating in isolated emptiness. It may be one bubble in a frothing sea of other universes, a vast cosmic foam where each bubble has its own distinct physics. If another universe, unimaginably large and massive, exists relatively close to ours in a higher dimensional space, its gravitational influence could reach across the void and pull on the matter within our cosmic bubble. Think of it like two soap bubbles floating near each other on the surface of water. Even though they are separate, the gravity of the larger bubble could subtly distort the shape and motion of the smaller one. In this scenario, the dark flow is our universe responding to the gravitational tide of a neighboring reality. We are like sailors on a ship feeling the pull of a massive, hidden whirlpool just over the horizon, a force we cannot see but whose effects are undeniable. This idea turns the cosmic horizon from a simple limit of observation into a tantalizing curtain, hiding the architecture of a grander multiverse. The dark flow remains controversial, with some scientists proposing alternative explanations or questioning the data analysis. Yet, if it holds true, it provides our first potential empirical evidence that our universe is not alone. We may be living in a cosmos that is, quite literally, being dragged towards something else. That immense gravitational pull from a neighboring universe is a force acting upon our own. But what if the most destructive force in the cosmos is not an outside pull, but an internal pressure, a kind of cosmic anti-gravity woven into the fabric of empty space itself? This brings us to the most violent possible end for all things, a theory known as the Big Rip. To understand it, we must confront the greatest mystery in modern cosmology, dark energy. For decades, we believed the universe's expansion was slowing down, gradually coasting from the force of the Big Bang. Then, in the late 1990s, astronomers made a shocking discovery. By observing distant supernova, they found that the expansion is not slowing at all. It is accelerating. Something is pushing galaxies apart faster and faster over time. That something is called dark energy, an enigmatic repulsive force that makes up about 68% of the entire universe. We do not know what it is, only what it does. It acts as a kind of negative pressure within the vacuum of space itself, causing the cosmos to swell at an ever-increasing rate. Now, the standard model of dark energy, called the cosmological constant, suggests this acceleration is steady and eternal. The universe would expand forever, growing cold and dark, with galaxies drifting apart into isolated loneliness. But there is a far more terrifying possibility. What if dark energy is not constant? What if it gets stronger over time? Physicists have given this hypothetical, ultra-powerful form of dark energy a fittingly ominous name: phantom energy. Unlike the gentle push of the cosmological constant, phantom energy would behave like a cosmic infection that grows in potency as the universe expands. The more space there is, the more phantom energy exists, and the harder it pushes, creating a runaway feedback loop of expansion. This leads to one inevitable, gruesome conclusion: the Big Rip. In this scenario, the accelerating expansion would not just pull galaxies apart. It would overcome every force that holds the universe together, from the largest scales down to the very smallest. First, the phantom energy's grip would shred the cosmic web, tearing galaxy clusters away from each other. Then, as the acceleration becomes unimaginably intense, it would rip individual galaxies apart. Stars would be plucked from their orbits and flung into the endless, growing void. Next, the expansion force would become stronger than the gravity holding our own solar system together. Planets would be torn from their suns. Then, it would grow stronger than the gravity holding Earth itself together. Our planet would be blasted into fragments. The horror would not stop there. As the phantom energy's power continued to increase exponentially, it would finally overcome the forces that bind atoms together. In the last fraction of a second before the end, every molecule, every atomic nucleus, and every fundamental particle would be violently ripped apart from every other. The universe would not end with a whimper of cold emptiness, but with a scream of ultimate disintegration, leaving behind a lifeless, featureless sea of lonely particles unable to ever interact again. The timeline for such an event depends on the strength of the phantom energy. In some models, the Big Rip could occur in as little as 22 billion years from now. On a cosmic scale that is not very far away, it is a deadline written in the shadow of a mystery. Currently, there is no direct evidence that dark energy is phantom energy. Our observations still fit the simpler, constant model, but the possibility remains, a lurking variable in our equations that suggests the ultimate fate of all reality could be one of total, unstoppable annihilation from within. It is a reminder that the vacuum of space is not truly empty. It may contain the seeds of our final destruction, a silent phantom waiting in the dark. But what if our entire understanding of cosmic forces is fundamentally wrong? For over a century, gravity has been the undisputed architect of the universe, the invisible hand that sculpts galaxies and guides the orbits of planets. Yet a radical and controversial school of thought challenges this gravitational monopoly. It is called the electric universe theory. This model proposes that the dominant force shaping the cosmos is not gravity, but electromagnetism, the same force that powers lightning and holds atoms together. Proponents argue that we live in a plasma universe, where 99% of all visible matter is not in the form of stars or planets, but in a fourth state of matter known as plasma. Plasma is an electrified gas, a soup of charged particles that conducts electricity and responds powerfully to electromagnetic fields. In this view, the vast filaments connecting galaxy clusters are not just strands of dark matter, but colossal cosmic-scale electrical currents flowing through the universe like circuits in a machine of unimaginable size. The theory suggests that galaxies themselves are not formed slowly by the collapse of gas under gravity, but are born from titanic electromagnetic pinches or Z-pinches within these intergalactic currents. Picture a lightning bolt but scaled up to the size of 100,000 light-years. These cosmic discharges, they argue, could spin vast clouds of plasma into the spiral arms of galaxies and ignite stars at their centers like beads on a wire. Stars in the electric universe model are not powered solely by internal nuclear fusion, but are fed by vast electrical currents flowing through space. A star is seen as a glowing anode in a galactic circuit, its brightness and behavior dictated by the electrical power it receives. This could explain bizarre stellar phenomena that gravity alone struggles with, like the extreme heat of the sun's corona or the unpredictable eruptions of certain stars. They point to the similarities between galactic structures and laboratory plasma experiments, where electrified gas naturally forms spinning disks, filamentary structures, and glowing balls that look eerily like miniature galaxies and stars. The most controversial claim of the electric universe theory strikes at the very heart of modern cosmology, the expansion of the universe itself. Edwin Hubble's landmark discovery was based on redshift, the observation that light from distant galaxies is stretched toward the red end of the spectrum. The standard interpretation is that this redshift is a Doppler effect caused by galaxies rushing away from us as space expands. But electric universe proponents offer a different explanation called tired light. They suggest that light could lose energy, and thus redshift, simply by interacting with matter or fields in the interstellar and intergalactic medium over its immense journey. If true, this would mean redshift is not a reliable measure of velocity or distance. A highly redshifted object might not be extremely far away or moving quickly. It might just be its light has been sapped of energy. This single idea, if validated, would dismantle the entire edifice of the Big Bang cosmology, the expanding universe, and the need for dark energy to explain acceleration. The scientific mainstream overwhelmingly rejects the electric universe model. Critics argue it fails to make precise, testable predictions that match astronomical data as well as the standard model of gravity and cosmology. They point out that the equations of electromagnetism are well understood and cannot, on their own, account for the orbital motions of planets or the stability of galaxies without the dominant role of gravity. The tired light hypothesis, they note, has been repeatedly tested and fails to explain other observed properties of distant starlight. Yet the theory persists on the fringes, a testament to the enduring human desire to question foundational assumptions. It asks a profound and unsettling question. Have we been reading the universe's story in the wrong language, focusing on the gentle pull of gravity while missing the crackle and flash of a cosmos alive with electric fire? The crackle of electric currents offers a radical alternative to our cosmic story, but there is another grand narrative that once stood as the Big Bang's greatest rival. It is a vision of an eternal, unchanging universe, one that requires no explosive birth and no ultimate death. This is the steady-state theory. In the mid-20th century, as evidence mounted for an expanding universe, a trio of brilliant scientists, Fred Hoyle, Thomas Gould, and Hermann Bondi, proposed a profoundly elegant idea. They accepted that space was expanding, but rejected the notion of a singular beginning. Instead, they argued the universe has always existed and will always exist, looking roughly the same at any point in time. There was no Big Bang, no moment of creation. The cosmos was infinite in both space and time. This presented an immediate puzzle. If galaxies are constantly drifting apart due to expansion, the universe would become more and more dilute, its density forever dropping. The steady-state model offered a stunning solution: continuous creation. The theory proposed that new matter, primarily hydrogen atoms, is spontaneously and slowly created out of nothing in the empty voids between galaxies. This creation happens at an almost imperceptible rate, just a few atoms per cubic kilometer every century, but it is enough to exactly balance the thinning caused by expansion. As old galaxies move apart, new material condenses to form new galaxies, maintaining a perfect cosmic equilibrium. The universe, in this view, is like a flowing river that always looks the same, even though the water molecules themselves are constantly moving and being replaced. Fred Hoyle, a vocal and charismatic proponent, famously coined the term Big Bang during a radio broadcast, intending it as a dismissive label for what he saw as an unscientific creation myth. For him, the steady state was more philosophically pleasing, a universe without a beginning or end, obeying the perfect cosmological principle where the laws of physics are constant everywhere and for all time. The theory's elegance made it a serious contender for decades. Its downfall came from a faint, cold whisper from the depths of space. In the 1960s, Arno Penzias and Robert Wilson accidentally discovered a uniform microwave static coming from every direction in the sky. This was the cosmic microwave background radiation, the cooled remnant of the universe's hot, dense early phase, precisely predicted by Big Bang cosmologists. It was the afterglow of the primordial fireball, a relic that the steady-state theory could not adequately explain without awkward modifications. This discovery was the decisive evidence that shifted the scientific consensus overwhelmingly toward the Big Bang. Yet the spirit of the steady-state never completely died. Modified versions, like the quasi-steady-state model, have been proposed to incorporate the background radiation, and the core idea of a universe in a kind of eternal balance still whispers from the shadows of cosmology. It challenges us to ask whether our need for a definitive beginning is a limitation of our minds rather than a feature of the cosmos. Perhaps the universe is not a story with a first page, but an endless poem being written one atom at a time. The steady state envisioned a universe without boundaries, but there is a different kind of boundary that may already contain us. We are now inside a black hole. This is not a metaphor for cosmic doom, but a serious mathematical proposal that our entire observable universe could be the interior of a colossal black hole residing in a much larger parent cosmos. The idea emerges from a stunning symmetry hidden within the equations of general relativity. Physicists noticed that the mathematical description of the universe's expansion from a Big Bang singularity looks eerily similar to the equations describing the spacetime geometry inside a collapsing black hole. Both begin with a singularity, a point of infinite density, and both describe a rapidly stretching fabric of space. In a collapsing star, everything is pulled inward toward the central crush. But for an observer falling into that black hole, their perspective is different. From inside, as they cross the event horizon, space itself can appear to be expanding outward from the singularity behind them. This internal expansion can, mathematically, mirror the expansion of our own cosmos. This leads to a breathtaking inversion of perspective. What we experience as the outward rush of galaxies from a Big Bang could be the inward plunge of spacetime within a black hole seen from the inside. Our cosmic horizon, the farthest point we can possibly observe, might not be a limit of our telescopes, but the literal event horizon of this encompassing black hole. We are not looking out into an infinite void. We are looking inward toward the center of our own cosmic prison, with the true, larger universe forever hidden behind the ultimate veil. Think of it like being in a vast, expanding room with walls that are receding at the speed of light. You can never reach the walls, and you can never see what is outside them. That room is our universe, and those walls are the event horizon. Everything we call the cosmos, from the smallest atom to the most distant galaxy, is contained within the interior of this unimaginably large celestial object. This theory provides a compelling, if unsettling, answer to a fundamental question: why did our universe begin? It did not begin from nothing. It began when a massive object in another universe collapsed, and we are the result. Our Big Bang was the formation of that black hole's interior. This also offers a potential explanation for the uniformity of the cosmic microwave background. The smooth, even temperature we see in that ancient light could be the result of our universe's interior reaching a state of thermal equilibrium, much like the inside of a sealed, chaotic system eventually evening out. The implications spiral outward. If our universe is a black hole, then every black hole within our own cosmos could itself contain an entire universe, a nested series of cosmic realities like a set of Russian dolls. And our parent universe likely has its own parent in an infinite regress of creation. We are not at the top of a cosmic chain, but somewhere in the middle, a link in an endless cycle where universes are born from the graves of stars in other realities. This idea transforms the black hole from a symbol of finality into a cradle of existence. It suggests that creation and destruction are two sides of the same coin, forever spinning in the dark. This endless cycle of cosmic birth within black holes offers a strange kind of immortality for universes, but what about for you? A startling idea from quantum mechanics suggests your own consciousness might never experience an end. This is the theory of quantum immortality, a mind-bending thought experiment that emerges directly from the many worlds interpretation. If every possible outcome of every quantum event occurs in a branching universe, then from a purely subjective point of view, a conscious observer will always find themselves in a reality where they continue to exist. Death in this framework is not an absolute cessation, but a branching point you simply never experience. To understand this, consider a grim but clarifying device called the quantum suicide machine. Imagine a setup where a gun is pointed at your head, triggered by the random decay of a single radioactive atom. In any given second, there is a 50% chance the atom decays and fires the gun, and a 50% chance it does not. According to the Copenhagen interpretation, you run the experiment once, and you have an equal chance of living or dying. The wave function collapses to one outcome. But in the many worlds view, the universe splits at the moment of measurement. In one branch, the atom decays, the gun fires, and you die. In the other, perfectly real branch, the atom does not decay, and you survive. Now, from the perspective of your conscious experience, which branch do you find yourself in? You can only be aware of the realities in which you are alive to have an awareness. The version of you that dies has no subsequent experience. So, from your first-person viewpoint, no matter how many times you pull the trigger, you will always find yourself in the universe where the gun did not fire. You would witness the mechanism click harmlessly again and again, a statistical impossibility that becomes your personal reality. This logic extends beyond dramatic experiments to every mortal danger in life. A car crash, a falling piano, a deadly virus in a vast multiverse, there will always be branches where you miraculously survive. Quantum immortality suggests your stream of consciousness is tethered to those branches, hopping from one timeline to the next whenever death looms, forever skipping over the realities where your story ends. The implications are as profound as they are unsettling. It proposes a form of subjective eternity where you could potentially live for billions of years, witnessing the heat death of the universe in one branch, only to continue into another where conditions allow life to persist. Your personal identity becomes not a single life story, but the singular thread of awareness that weaves through the infinite tapestry of the multiverse, always avoiding the snipped ends. This forces a difficult question about the nature of death. Is it a universal truth or merely a separation? The people around you would still experience your death in countless branches, mourning a loss that the version of you they never encounter does not share. You would become a ghost in the machinery of reality, forever out of sync with the loved ones in any one world. While this is a philosophical exploration rather than a testable scientific theory, it highlights the profound strangeness of linking consciousness to quantum probability. It suggests that in a universe of infinite possibilities, the one thing you may never encounter is your own final moment. The unsettling notion of a consciousness that never ends stems from the quantum world's refusal to make a final choice. Yet this same quantum realm is locked in a bitter war with gravity over the ultimate fate of information itself. This conflict is the black hole information paradox, and it represents one of the most profound puzzles in all of theoretical physics. It is a battle between two pillars of modern science, general relativity and quantum mechanics, and the battlefield is the edge of a black hole. According to Einstein's theory of gravity, a black hole is defined by its event horizon, a point of no return. If you cross this boundary, you are inexorably pulled toward the central singularity. To the outside universe, all information about you, your mass, your atomic structure, your memories, is lost forever behind that dark curtain. The black hole retains only three simple properties: its mass, its electric charge, and its spin. From the perspective of general relativity, this is fine. The information is not destroyed, it is just hidden, trapped inside in a state we can never access. But quantum mechanics, the rulebook for the subatomic world, has a sacred, unbreakable law. Information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must be preserved in principle. If you burn a book, the ash and smoke still contain, in an incredibly complex way, the information needed to reconstruct every word. Quantum mechanics insists the universe must keep a perfect record. Stephen Hawking's revolutionary work in the 1970s made this conflict unavoidable. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly leak radiation and evaporate over unimaginable eons. This Hawking radiation, however, appeared to be purely thermal, random noise carrying no information about what fell in. The terrifying implication was this: when a black hole finally evaporates completely, all the information about the stars, planets, and people it ever consumed would vanish from the universe forever. The cosmic ledger would be erased. This is the paradox. General relativity says information is hidden. Quantum mechanics says it must be preserved, and Hawking's calculations suggested it is obliterated. Physicists have been wrestling with this for decades, and their proposed solutions are as bizarre as the paradox itself. One leading idea returns us to the holographic principle. It suggests the information of everything that falls into the black hole is not lost inside, but is smeared and encoded in a scrambled, two-dimensional form on the event horizon itself. The three-dimensional interior is a projection from this data. When Hawking radiation is emitted, it slowly and chaotically carries that encoded information back out into the universe, like a shredded document being painstakingly reassembled one photon at a time. The information is never truly lost, just incredibly difficult to decode. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth gateway, but a searing wall of ultra-high energy particles. The moment you touch it, you are incinerated. This firewall would resolve the paradox by preventing any information from actually entering the black hole in the first place, but it violates Einstein's principle that crossing the horizon should be uneventful. It trades one paradox for another. A more recent and mind-bending proposal is the idea of quantum entanglement playing a key role. Perhaps the particles of Hawking radiation are subtly entangled with the information inside or with each other, creating a complex web that preserves the data. The information escapes, but in a form so tangled and non-local that it looks like random noise until the very last moments of the black hole's evaporation. Each solution has profound consequences for our understanding of reality. The holographic principle suggests that information is the true fundamental substance of the cosmos. The firewall idea hints that our smooth picture of spacetime completely breaks down at the horizon. This paradox is not just an academic exercise. It forces us to ask what truly happens to the past, to history, when it meets the most extreme gravity in the universe. Is the cosmos a perfect recorder, or does it allow for permanent erasure? The answer will likely require a new theory of quantum gravity, a framework that can finally reconcile the warring laws of the very large and the very small. Until then, the black hole stands as the universe's ultimate shredder, and we are still not sure if the shreds can ever be pieced back together. The paradox of information lost in a black hole is a cosmic mystery, but it pales before a silence that fills the entire sky. Given the sheer number of stars and planets, the universe should be teeming with life. So why do we hear nothing at all? This profound contradiction is the Fermi Paradox, named for physicist Enrico Fermi, who, during a casual lunch conversation in 1950, posed a devastatingly simple question. Where is everybody? The numbers are overwhelmingly on the side of existence. Our galaxy alone contains hundreds of billions of stars, most with planets. Even if only a tiny fraction of those planets are Earth-like, and only a minuscule fraction of those develop life, and only a sliver of those evolve intelligent civilizations, the math still suggests the Milky Way should be home to thousands, if not millions, of advanced societies. Some should have arisen millions of years before us, giving them more than enough time to colonize the entire galaxy. Their spacecraft or probes should be everywhere. Their radio signals, their energy signatures, their megastructures should be unmistakable. Yet our telescopes scan the heavens and find only a vast, unbroken quiet. This eerie silence is the heart of the paradox. To explain it, scientists have proposed dozens of solutions, from the optimistic to the terrifying. Perhaps civilizations are simply too far apart in space and time to ever make contact. Maybe they communicate in ways we cannot yet perceive, using neutrino beams or quantum entanglement. It is possible they observe a strict policy of non-interference, a galactic prime directive, leaving primitive worlds like ours in peaceful isolation. Or perhaps they have transcended physical form, uploading their consciousness into virtual realities, leaving the barren universe behind. But one explanation stands out for its grim, sobering implications. It is called the Great Filter. The theory suggests that the evolution of life from simple chemistry to a galaxy-spanning civilization is not a smooth path. Somewhere along that journey, there exists an evolutionary or technological barrier so extreme, so difficult to overcome, that it filters out nearly every species that attempts it. This barrier is the Great Filter, The critical, haunting question is, where does this filter lie? Is it behind us or ahead of us? If the filter is in our past, it means we have already passed through a cosmic bottleneck that almost no other species survives. This would make humanity extraordinarily rare and lucky. Perhaps the jump from non-living chemistry to simple, replicating life is astronomically improbable. Or maybe the leap from single-celled organisms to complex, multicellular animals is the true miracle. If this is the case, the universe might be filled with sterile worlds and dead microbial mats, with intelligent life vanishingly scarce. We would be a cosmic accident, alone but safe. The alternative is far more disturbing. What if the great filter still lies in our future? This is the warning. It suggests that the step from our current technological adolescence to a stable, interstellar civilization is the one that proves fatal for everyone. The filter could be any number of existential catastrophes that we are now engineering for ourselves. It might be the invention of artificial intelligence that turns against its creators. It could be the unleashing of biotechnology that creates an unstoppable pandemic. It might be nuclear war, climate collapse, or the unforeseen consequences of nanotechnology running amok. Or it could be something we have not even conceived of yet, a danger that only reveals itself when a species reaches a certain level of technological prowess. In this scenario, the silence of the cosmos is a cemetery. Every civilization that reaches our stage of development ultimately destroys itself, leaving behind only ruins and radio waves that fade into the void. The Fermi Paradox, then, is not a puzzle but a countdown clock. Our failure to detect anyone else could be the most important data point in human history, a sign that the hardest step is not becoming smart but surviving your own intelligence. As we push toward the stars, we are not just exploring space. We are running an experiment to see if any species can make it through the filter that seems to have silenced all the others. The quiet sky is either a testament to our incredible luck or the universe's loudest warning. That profound silence might not be a warning, but a deliberate choice made by those watching us. If the universe is so vast and old, and we are so loud and visible, our continued isolation feels less like an accident and more like a policy. This leads to a compelling and strangely peaceful solution to the Fermi Paradox, the zoo hypothesis. It proposes that advanced extraterrestrial civilizations are not just out there, they are fully aware of our existence. They have detected our radio signals, observed our biosphere, and monitored our technological growth. Yet, they have made a collective, ethical decision to avoid all contact, placing Earth under a form of cosmic quarantine. In this view, our planet is a protected wilderness area, and humanity is a fascinating but primitive species to be studied from a distance, like animals in an immense galactic zoo. The motivation is not malice but preservation. A civilization that has survived for millions of years would understand the dangers of cultural contamination. Our entire history, our religions, our sciences, and our social structures are the products of our own unique, isolated evolution. Direct contact with a vastly superior intelligence would shatter that development. It would be the ultimate cultural shock, likely causing our society to collapse or permanently stunting our intellectual and spiritual growth. We would forever be in their shadow, our own potential cut short. To prevent this, they maintain a strict non-interference protocol, a real-world version of science fiction's prime directive. They watch, they listen, and they ensure no other species disturbs us either. This creates a quiet bubble around our solar system, a silent gallery where we are the exhibit. The philosophical implications of this are deep. It suggests a galactic community bound by a profound ethical code, one that values the natural evolution of consciousness above all else. They may be waiting for us to reach a specific milestone, perhaps the discovery of a unified theory of physics, the achievement of sustainable planetary peace, or our first successful interstellar voyage, before they consider us mature enough for an introduction. Until then, we are like children in a playground, unaware that wise, patient guardians are observing from just beyond the fence, ensuring we learn our lessons without outside help. This hypothesis reframes our search for extraterrestrial intelligence. We may not find them because they do not wish to be found by us. Our radio telescopes might be picking up the equivalent of one-way mirrors, and our probes could be passing through territories carefully designed to seem empty. The silence is not empty at all, it is curated. It is the sound of being studied with infinite patience, a quiet that speaks of a universe far more thoughtful and far more mysterious than we ever dared to dream. The quiet observation of a galactic zoo suggests we are a protected experiment, but what if the experiment began long before humanity ever walked the Earth? Our next theory proposes that life itself is not a local phenomenon, but a cosmic traveler. This is the idea of panspermia. It suggests the seeds of life, in the form of hardy microorganisms, are present throughout the universe, hitching rides on asteroids, comets, and cosmic dust. When these celestial bodies crash into young planets, they deliver the biological starter kit, planting life in new soil. The concept elegantly solves a puzzle on our own world. Life appeared on Earth surprisingly quickly after the planet cooled, in a relatively narrow window of time. Some scientists argue that the complex chemistry needed for the first living cell might have required more time to develop from scratch. Panspermia offers an alternative timeline. The building blocks, or even primitive life itself, could have been brewing in interstellar space for billions of years, arriving here fully formed during the late heavy bombardment, when the young Earth was pelted by countless asteroids and comets. We have compelling evidence that life is astonishingly tough. We find microorganisms called extremophiles thriving in places once thought utterly sterile, in boiling hydrothermal vents, in the crushing depths of the ocean, locked in ancient Antarctic ice, and even in the highly radioactive environment of nuclear reactor cooling pools. If life can survive these conditions on Earth, could it not survive a journey through space, shielded within the heart of a rocky meteorite? Experiments on the International Space Station have shown that certain bacteria and lichen can indeed survive for years in the vacuum and radiation of low Earth orbit, lending credence to the idea that life could be a cosmic stowaway. But this theory has an even more provocative cousin, one that moves from accidental seeding to deliberate gardening. This is directed panspermia. The Nobel Prize-winning co-discoverer of the structure of DNA, Francis Crick, along with chemist Leslie Orgel, seriously proposed this idea in the 1970s. They suggested that the origin of life on Earth was not a random accident of chemistry, nor a passive delivery by space rocks. Instead, they argued it could have been a deliberate act of biological seeding by an advanced extraterrestrial civilization. In this scenario, our planet was chosen, and a capsule containing primitive microorganisms was sent here on a spacecraft, perhaps to ensure the spread of life throughout the galaxy. Crick and Orgel were not indulging in fantasy. They were grappling with the same puzzle of life's rapid appearance. Directed panspermia to them was a scientific hypothesis that answered a difficult question. Why does all life on Earth share the same intricate, complex genetic code? Could this universal language be a signature of the original seed, a designed system planted here long ago? The idea transforms our origin story. Humanity would not be the random product of a lonely planet's chemistry, but the distant descendant of a purposeful act of creation from the stars. We would be part of a grand, galactic experiment in biodiversity, or perhaps even the heirs to a legacy we do not yet understand. Whether life arrived by chance or by design, panspermia reshapes our place in the cosmos. We are not necessarily natives of Earth, but possibly citizens of a much larger, living universe, connected to every corner of the galaxy by threads of DNA older than our Sun. The peaceful silence of a galactic zoo is a comforting thought, but there is a far more terrifying explanation for the quiet. It comes not from a scientific paper, but from a work of science fiction that has since haunted the halls of serious discussion. This is the dark forest hypothesis, a chilling answer to the Fermi Paradox that paints the cosmos not as a community, but as a deadly game of survival. The metaphor is stark and unforgettable. Imagine the universe as an immense, pitch-black forest. You are a hunter, alone and afraid. You know other hunters are hiding among the trees, but you cannot see them and you do not know their intentions. Every hunter is armed. In this forest, the first rule of survival is absolute silence. To make a sound, to light a fire, is to reveal your location, and any other hunter who hears you cannot afford to assume you are friendly. The safest, most logical course of action is to immediately fire a shot in the direction of the sound, eliminating a potential threat before it can ever become a danger to you. In this cosmic analogy, every civilization is a hidden hunter. The forest is the dark void of space, and the sound is any signal, any broadcast, any detectable sign of a technological society. The hypothesis argues that the universe appears silent not because civilizations are rare or because they are watching us peacefully, but because they are all deliberately hiding, terrified of being discovered. Any civilization that grows advanced enough to look at the stars will eventually realize this grim logic. The history of their own planet teaches them that life expands and competes for finite resources. When they look outward, they face what philosophers call the chain of suspicion. You cannot know the intentions of another civilization 1,000 light years away. They might be peaceful, but you cannot be sure. Even if they are peaceful now, they might change. Even if they promise peace, you cannot trust them. The only way to guarantee your own civilization's survival in the long, dark night of cosmic time is to preemptively destroy any other civilization you detect before it can ever become powerful enough to do the same to you. This makes broadcasting our existence, as we have done for over a century with radio and television signals, an act of potentially catastrophic folly. In the dark forest, we are not the zookeepers. We are the child in the woods shouting our name and waving a flashlight, utterly unaware of the silent hunters who may now be taking aim. This theory takes the great filter and makes it active and ongoing. The filter is not a single event in a civilization's past, but a permanent state of galactic geopolitics. The reason we see no grand engineering projects, no interstellar empires, is not because they are impossible. It is because any civilization that becomes that visible makes itself the brightest target in the forest. The most successful, long-lived civilizations are likely the quietest, the most stealthy, the ones that have learned to cloak their energy signatures, to hide their worlds, and to listen without ever replying. It is a universe where paranoia is the highest form of intelligence. The dark forest is a bleak and lonely answer, but it is a logically consistent one. It explains the silence perfectly, and it suggests that our efforts to search for extraterrestrial intelligence, to beam messages to the stars, might be the most dangerous experiment humanity has ever undertaken. We are essentially shouting into the darkness, hoping for a friend, while assuming every other voice in the void is a potential predator. The terrifying truth may be that in the dark forest there are no friends, only survivors, and the first rule of survival is to never, ever answer. The dark forest is a universe of silent, paranoid minds, but what if the mind itself is not a product of the brain, but of the universe? This brings us to one of the most controversial theories in all of science, the quantum consciousness theory. Proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, it suggests that our awareness, our very sense of self, is not simply the result of classical chemical and electrical signals firing in the brain. Instead, they argue, consciousness emerges from delicate quantum processes happening deep within our neurons, inside structures called microtubules. These are the tiny scaffolding proteins that give cells their shape. Penrose and Hameroff propose that these microtubules are not just structural. They could act as quantum computers where particles exist in superpositions, performing calculations that give rise to the rich, unified tapestry of conscious experience. The theory, called orchestrated objective reduction, posits that these quantum superpositions inside microtubules grow until they reach a threshold, then collapse in a coordinated way. Each collapse is a moment of conscious experience, a quantum blip of awareness that strings together into the flow of thought. This would explain why consciousness feels so immediate and non-algorithmic, different from the step-by-step processing of a classical computer. It links the mysterious world of quantum mechanics directly to the mystery of subjective experience, but the implications reach far beyond biology. If consciousness is rooted in quantum physics, then it might not be an accidental byproduct of complex computation. It could be a fundamental feature of the cosmos, as basic as space, time, and matter. In this view, the universe is not a cold, dead machine, but possesses a proto-consciousness woven into the fabric of spacetime itself. The quantum processes in our brains might simply be tapping into this fundamental field of awareness, like a radio tuning into a broadcast that exists everywhere. This radical idea, known as panpsychism, suggests that consciousness did not evolve. It was always here. It is a property of reality that becomes organized and amplified in complex systems like the human brain. This leads to a staggering possibility. If consciousness is quantum and fundamental, could it affect reality? The observer effect in quantum mechanics shows that the act of measurement forces a particle to choose a definite state. Some interpretations suggest consciousness itself is what causes the wave function to collapse, that reality remains in a haze of possibilities until a conscious mind observes it. While mainstream physics heavily disputes this, the quantum consciousness theory forces us to reconsider our place in the cosmos. We are not just passive observers of a predetermined universe. We might be active participants, our very awareness playing a subtle but real role in shaping the reality we perceive. Our minds could be quantum instruments, not just reading the cosmos, but in some small way writing it with every thought we have. That quantum link between mind and cosmos depends on a stage where all events are fixed. Our next theory dismantles the very stage itself, the illusion of time. According to Einstein's theory of relativity, the distinction between past, present, and future is nothing but a stubbornly persistent illusion. Time is not a river flowing from a source to a sea. It is a dimension as real and as static as the three dimensions of space. This is the block universe theory. Picture all of existence, from the Big Bang to the heat-death of everything, not as a sequence of moments, but as a single, immense four-dimensional block. Within this block, every event that ever was or ever will be has a fixed location. Just like every city has a fixed location on a map, your birth, your reading of this sentence, and your last breath all exist eternally within this cosmic structure. They are all equally real. The feeling that time passes, that the future is open and the past is gone, is a trick of our consciousness, a psychological artifact of how our brains process information in a single, winding path through this eternal block. We are like a needle on a record player, experiencing one groove at a time and calling it the present, while the entire song already exists on the vinyl. This idea emerges directly from Einstein's equations, which treat time as a coordinate woven together with space into a single fabric called spacetime. In this view, there is no universal now. What is the present for you on Earth is the past for an observer on a distant star and the future for someone traveling near a black hole. Simultaneity is relative. The block universe makes this permanent, declaring that all those perspectives are simply different slices through the same unchanging loaf of reality. Yet this creates a profound tension with our lived experience and with other laws of physics. Why do we remember the past but not the future? This is where the arrows of time come in. The thermodynamic arrow points in the direction of increasing disorder, from a state of low entropy to high entropy. We see an egg smash on the floor, but we never see the pieces spontaneously reassemble. This gives time a clear direction, an asymmetry that the block universe alone does not explain. Then there is the quantum arrow related to the collapse of the wave function, which also seems to proceed in one direction. These arrows create the appearance of a flow, a one-way street through the static block. So which is more fundamental? Is the block universe the true reality, with the arrows of time being emergent properties of our local corner of it? Or is our powerful sense of a flowing present a clue that the block is incomplete? This theory forces a deeply personal question. If the future is already out there, fixed in the block, then what becomes of free will? Are our choices an illusion, a script we are simply reading as we move along our world line? Or does consciousness itself, moving through the block, somehow select the path? The block universe theory does not offer comfort. It offers a cold, beautiful, and unsettling truth from the mathematics of reality, suggesting that our most intimate experience, the passage of time, is the grandest magic trick the universe plays on our minds. If time is a static block, then what animates our journey through it? Perhaps the answer lies not in the structure of spacetime, but in a quality inherent within it. Some of the greatest minds in physics and philosophy have revived an ancient idea, one that suggests the universe is not a dead machine, but a living, conscious entity. This is panpsychism, the theory that consciousness is a fundamental property of reality, as basic as mass or electric charge. In this view, mind did not mysteriously emerge from mindless matter. Instead, some form of experience, however simple, has been here from the very beginning. The theory proposes that even the most fundamental particles, like electrons or quarks, possess a tiny spark of subjective experience, a raw feeling of existence. A rock would not be conscious in the way we are, but the particles within it might have a primitive, isolated form of awareness. When these particles combine into increasingly complex systems, like neurons in a brain, these micro-experiences could combine and integrate, giving rise to the rich, unified stream of consciousness you are experiencing right now. Panpsychism directly tackles what philosophers call the hard problem of consciousness. This is the question of why and how physical processes in the brain, the firing of neurons and the flow of chemicals, give rise to subjective experience, the taste of chocolate, the feeling of love, or the color red. Science can map the brain's activity, but it cannot explain why that activity feels like anything at all. Panpsychism offers an elegant, if radical, solution. It says subjective experience does not emerge from complexity. It is already there in the ingredients. The brain does not create consciousness. It organizes and amplifies it, like an orchestra conductor turning individual notes into a symphony. This idea finds startling echoes in modern cosmology and the puzzle of fine-tuning. Our universe's physical constants, like the strength of gravity or the mass of an electron, appear exquisitely balanced to allow for the existence of stars, planets, and life. If any of these numbers were even slightly different, complex structures would be impossible. The traditional explanations are a multiverse, where every possible value exists somewhere, or a divine creator. Panpsychism suggests a third, mind-bending possibility. What if a universe becomes finely tuned for complex life because, on some fundamental level, it possesses a desire to know itself? If consciousness is woven into the fabric of reality, then the cosmos might not be a random accident. It could be a system evolving toward greater and greater levels of integrated awareness, with stars, planets, and living beings as its instruments of self-exploration. In this view, we are not just conscious beings in the universe. We are the universe becoming conscious of itself, localized points where the cosmos wakes up and looks around. This transforms our loneliness into a profound connection. Every particle in every distant galaxy shares, in some infinitesimal way, in the same fundamental quality that allows you to wonder about it. The silence of the cosmos is not empty. It is the quiet hum of a universe slowly, patiently coming awake. That profound cosmic awakening might unfold through a process far more violent than a gentle expansion. Our universe could be the scar from a titanic collision in a higher dimension. This is the ekpyrotic universe model, a radical alternative to the standard Big Bang story that replaces the primordial singularity with a shattering impact. The theory emerges from the mathematics of string theory, which suggests our reality is not confined to the three dimensions we experience. Instead, we may live on a three-dimensional membrane, or brain for short, floating within a higher dimensional realm called the bulk. Picture our entire cosmos as a vast, three-dimensional sheet, like a page in an unimaginably large book. Now, imagine another cosmic sheet floating parallel to ours in the bulk. According to the ekpyrotic model, our Big Bang was not a moment of creation from nothing. It was the moment these two immense, multidimensional brains smashed into each other. The collision would have unleashed an unbelievable torrent of energy, heating our brain to an incredible temperature and filling it with the hot, dense plasma that became the seeds of all matter and radiation. This event set our cosmic history in motion, but without a true singularity of infinite density. The collision provides a clean, physical starting point that avoids the mathematical breakdown of general relativity at time zero. But the theory goes even further, offering a vision of cosmic rebirth. The ekpyrotic model is often part of a cyclical universe scenario. After the brains collide, they rebound and move apart, each carrying the debris of a newly formed universe that expands and cools much like our own. Over an immense epoch, the expansion slows, and the mutual gravitational attraction of the brains draws them back together. Eventually, they collide again, triggering a new Big Bang and resetting the cosmic clock. In this view, our universe is just one cycle in an endless, timeless series of cosmic collisions and expansions, a never-ending heartbeat of creation. This elegantly addresses the question of what came before the Big Bang. There was no before in a linear sense. There was only the previous cycle, another universe that expanded, cooled, and ultimately ended in a fiery collision that gave birth to our own. The model also proposes an explanation for the universe's startling uniformity. Before the collision, the two brains could have been nearly perfectly flat and parallel, stretching for eons. When they finally met, this smooth, uniform contact would have transferred energy evenly across the entire surface of our brain, explaining why the cosmic microwave background looks the same in all directions. It is a cosmic imprint of a perfectly aligned crash. While the ekpyrotic model is compelling, it remains highly speculative, a beautiful story written in the language of string theory that has yet to produce definitive, testable predictions different from standard inflation. Yet it offers a breathtaking narrative, one where the birth of everything we know was a moment of cataclysmic contact in a hidden, higher dimensional space, and where the end of our universe might simply be the prelude to another beginning in the dark bulk. That endless cycle of cosmic collisions offers a breathtaking vision of rebirth, but it leaves the vast distances between stars intact. To cross those gulfs, we would need to bend the rules of the cosmos itself. In 1994, physicist Miguel Alcubierre proposed a way to do exactly that, not by breaking the universal speed limit of light, but by cleverly manipulating the road it travels on. He found a theoretical solution within Einstein's own equations of general relativity that could allow for faster-than-light travel, the Alcubierre warp drive. The concept is deceptively simple. Instead of trying to propel a spacecraft through space at impossible speeds, you would move the space around the spacecraft. Alcubierre envisioned a warp bubble, a region of flat spacetime containing the ship, nestled between two profound distortions. In front of the bubble, spacetime would be massively contracted, pulled inward like a scrunched-up rug. Behind the bubble, spacetime would be drastically expanded, stretched outward. The bubble itself, with the ship inside, would then surf this wave of distorted spacetime. Since the ship is not moving through space locally within its bubble, it avoids the relativistic effects like time dilation and mass increase. It is the space itself that is moving, and general relativity places no speed limit on the expansion or contraction of spacetime. The ship could, in principle, be carried along at speeds many times faster than light. It is a brilliant loophole, turning the fabric of the universe into an engine. But creating such a warp bubble requires something truly bizarre, a form of matter with negative energy density, often called exotic matter. This is not just rare or unknown matter. It is matter that would possess negative mass, meaning it would gravitationally repel normal matter. You would need this exotic substance to compress the spacetime in front and expand it behind, shaping the warp bubble's walls. The energy requirements Alcubierre initially calculated were astronomical, on the order of the mass energy of an entire star, perhaps even a Jupiter-sized mass converted entirely into energy. For decades, this placed the concept firmly in the realm of speculative fiction, a beautiful mathematical idea with no physical way to build it, yet the dream did not die. In recent years, scientists at NASA, Eagleworks Laboratory, and other researchers have revisited the math, exploring ways to drastically reduce those energy requirements. Some calculations suggest that by oscillating the warp bubble or changing its shape, the needed negative energy could be brought down to the mass of a small spacecraft like the Voyager probe. Others are investigating whether effects in quantum field theory, like the Casimir effect, which creates a tiny negative pressure between two metal plates, could be harnessed to generate the necessary conditions on a microscopic scale. While we are still light years, pun intended, from building a working warp drive, this ongoing research represents a profound shift. It moves the concept from pure fantasy into the domain of theoretical engineering, a long-shot blueprint for a technology that could one day unite the stars. The Alcubierre drive is a testament to human ingenuity, a promise that the universe's own rules might contain the secret to crossing its greatest distances, if only we are clever enough to learn how to read them. The warp drive bends space itself, but what if the universe's most famous dark objects are not what they seem? For decades, black holes have been the ultimate endpoint of gravity, places where matter is crushed into a point of infinite density called a singularity. Yet singularities are where our laws of physics break down completely, a sign that our understanding is incomplete. Some theorists propose a radical alternative, an object that looks like a black hole from the outside but has a completely different heart. They call it a black star or a gravistar. Imagine a star collapsing under its own immense weight, just as it would to form a black hole. But instead of collapsing all the way to a singularity, the incredible pressure at its core triggers a phase transition. The matter inside transforms into something exotic, a bubble of dark energy. Dark energy, you will recall, is the mysterious force causing the universe's expansion to accelerate. It possesses a powerful negative pressure, a kind of cosmic repulsion. In the core of a gravistar, this repulsive force pushes outward with such strength that it perfectly balances the inward crush of gravity. The collapse stops, the star reaches a new, stable state, frozen just shy of forming a point of infinite density. It becomes a celestial object with a bizarre anatomy, a shell of incredibly dense, normal matter surrounding a core of pure dark energy. From a distance, a gravistar would be almost impossible to distinguish from a black hole. It would have an apparent event horizon, a point of no return for light. This is not a true event horizon where space-time is infinitely curved, but a boundary so extreme that light would take nearly an infinite amount of time to escape, appearing frozen to any outside observer. It would also pull in surrounding gas and dust, forming the same brilliant, swirling accretion disks we see around black holes. The gravitational lensing, the bending of light around it, would be identical. So why propose such a strange object if it acts the same? The answer lies in solving profound paradoxes. a gravastar neatly avoids the troublesome singularity, that point of infinite density where physics becomes meaningless. By halting the collapse, it keeps reality intact. More importantly, it could resolve the black hole information paradox. Since a gravastar has no true event horizon and no singularity, information about what falls in is not lost behind a one-way curtain or destroyed. Instead, it could theoretically be preserved on the star's ultra-dense shell or within its exotic interior, never truly erased from the universe. This offers a cleaner solution to the war between quantum mechanics and general relativity. While compelling, the gravastar remains a hypothetical idea. The phase transition to dark energy inside a collapsing star is purely speculative, and we have no known mechanism to create such a state. Detecting the subtle differences between a true black hole and a gravastar, perhaps through detailed observations of how their apparent horizons vibrate or interact with infalling matter, is a challenge for future telescopes. Yet it stands as a brilliant reminder that our universe might hide its true nature behind perfect disguises, and that the darkest objects in the sky could be guarding secrets far stranger than an endless fall into nothing. Gravastars offer one escape from the crushing grip of a singularity, but there is another path, one that rewrites the very beginning of everything. Our quest to understand reality at its most fundamental level has long been stymied by a great divide. On one side, we have quantum mechanics, the wildly successful rulebook for the subatomic world of particles and probabilities. On the other, we have Einstein's general relativity, the majestic description of gravity as the curvature of spacetime by mass and energy. Both are brilliantly accurate in their own domains, but they are written in completely different mathematical languages, and they break down when forced to meet. This clash becomes catastrophic in places of extreme gravity, like the center of a black hole or the first moment of the Big Bang, the infamous singularity. To heal this rift and describe the universe at its birth, physics needs a single, unified framework, a theory of quantum gravity. One of the most promising candidates is called loop quantum gravity. Unlike string theory, which proposes tiny vibrating strings in extra dimensions, loop quantum gravity takes a more conservative approach. It seeks to quantize spacetime itself, to treat the fabric of the cosmos not as a smooth, continuous sheet, but as woven from tiny, indivisible loops. Picture the universe not as a blank canvas, but as an incredibly fine mesh, a network of intersecting threads where each tiny loop is a fundamental unit of space. There is no such thing as a volume smaller than one of these loops, just as you cannot have half an atom. This introduces a fundamental granularity to reality, a pixelation of spacetime at the smallest possible scale, the Planck length. This quantum structure of space has a breathtaking consequence for cosmology, leading to a model called loop quantum cosmology. When we rewind the cosmic clock using these new equations, we approach the Big Bang. In the standard model, density and temperature soar to infinity as we reach the singularity. But in loop quantum cosmology, the quantum nature of spacetime intervenes. As matter and energy are compressed, they reach a point where the tiny loops of space are packed as tightly as possible. At this extreme density, a remarkable quantum effect emerges, a powerful repulsive force generated by the geometry of spacetime itself. Think of it like compressing a spring. You can push it down, but eventually it pushes back with equal and opposite force. In this cosmic model, gravity, which is always attractive, effectively becomes repulsive at these unimaginable densities. This repulsive force does not just stop the collapse, it reverses it. The collapsing universe hits this quantum barrier and bounces. Our Big Bang was not a beginning from nothing, but a transition, a great rebound from a previous cosmic phase that was contracting. This is the theory of the Big Bounce. In this view, our expanding universe was born from the collapse of a previous universe. That earlier cosmos may have looked very different from our own, with different constants and perhaps even different dimensions, but it followed the same cycle, expanding from its own bounds, living out its lifespan, and eventually succumbing to gravity's pull to contract once more. The singularity, that point of infinite density where physics breaks down, is never reached. The quantum structure of space provides a cushion, a cosmic trampoline that turns a catastrophic crunch into a glorious, explosive new beginning. This creates a cyclical picture of the cosmos, but with a crucial difference from older ideas. This is not an endless, identical repetition. Each bounce could reset or scramble the fundamental constants, meaning each new universe in the cycle might be born with entirely new laws of physics. Our universe, with its specific balance allowing for stars and life, could be just one fortunate roll of the dice in an endless sequence of cosmic rebirths. Loop quantum cosmology offers a profound and elegant vision, one where the universe has no true beginning or end in time, only eternal transformations, each birth written in the quantum grammar of spacetime itself. The quantum loops of a bouncing universe paint a picture of a fiery, dense origin, but that primordial fire left behind more than just light. There is another, far more elusive echo from the dawn of time, a whisper so faint we have yet to hear it. This is the cosmic neutrino background. We are all familiar with the cosmic microwave background, that faint afterglow of the Big Bang that fills the entire sky. It is the oldest light we can see, a snapshot of the universe when it was 380,000 years old, a hot, opaque plasma finally cooling enough for atoms to form and light to travel freely. But there is an even older relic, one that carries a message from a much earlier, more violent moment. 1 second after the Big Bang, the universe was a seething cauldron of energy, far too hot and dense for even atomic nuclei to hold together. In that maelstrom, particles called neutrinos were born in staggering numbers. These ghostly particles, with almost no mass and no electric charge, barely interact with normal matter. As the universe expanded and cooled over that first second, it reached a point where neutrinos stopped interacting frequently with the hot soup of particles around them. They decoupled, flying free into the expanding cosmos. This created a sea of primordial neutrinos that has been streaming through the universe ever since, cooling and stretching with the expansion of space, just like the cosmic microwave background photons did later. This is the cosmic neutrino background. It is a fossil from the universe's first second of existence, a direct snapshot of that unimaginably hot and dense infant cosmos. If we could capture it, it would be like having a photograph of the universe taken a mere heartbeat after its birth, 1 billion times earlier than the picture provided by the microwave background. So why have we not found it yet? The challenge is almost beyond comprehension. Neutrinos are famously aloof. Trillions of them from the sun are passing through your body every second, and nearly all of them travel right through the entire Earth without a single interaction. The primordial neutrinos from the cosmic neutrino background are even more elusive. They have been traveling for 13.8 billion years, and the expansion of the universe has stretched their energy to incredibly low levels. They are now ultra-cold, moving at speeds barely above a crawl. Detecting a single one of these ancient ghosts is like trying to hear a specific snowflake land in a blizzard while you are standing in the middle of a hurricane. Our current neutrino detectors are monumental feats of engineering, like the Super Kamiok, and in Japan or the Ice Cube Observatory buried in the Antarctic ice. But they are designed to catch high-energy neutrinos from violent cosmic events like supernova or active galactic nuclei. They are like nets built to catch tuna, utterly useless for detecting the faint, cold mist of the primordial neutrino sea. To have any hope, we would need a detector of unimaginable scale and sensitivity. Some proposals are almost science-fictional in scope, envisioning a device the size of a planet, using an entire moon or a vast volume of a special superfluid as the detection medium. The technical and financial hurdles are, for now, insurmountable. Yet the scientific prize is worth the impossible dream. Detecting the cosmic neutrino background would not just give us an earlier baby picture. It would allow us to peer into epochs completely hidden from traditional astronomy. Because neutrinos decoupled so early, they carry unaltered information about the conditions in the first second, a time when the universe was governed by forces and particles we can only theorize about today. They could tell us about the possible existence of heavy, exotic particles from grand unified theories, or provide clues about the asymmetry between matter and antimatter that allowed our universe to be made of something rather than nothing. Finding this ancient sea of ghosts would be the ultimate archaeological dig, reaching back to the very foundation of reality and sifting through the first whispers of creation. The faint sea of neutrinos is a relic of a smooth, uniform beginning, a cornerstone of modern cosmology. But what if the universe is not smooth at all? What if, when you zoom out far enough, you find not a featureless expanse but an endless, repeating pattern? This is the fractal universe hypothesis, a direct challenge to one of our most fundamental assumptions about the cosmos, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. It looks roughly the same in every direction and from every location. The matter is evenly distributed like a perfectly mixed batter. This idea is the foundation for our models of cosmic expansion, dark energy, and the Big Bang itself. But a small group of cosmologists, led by figures like Luciano Pietranero, have spent decades arguing this is an illusion. They propose that the distribution of galaxies and clusters is not uniform, but follows a fractal pattern, a kind of cosmic recursion where the same intricate shapes repeat themselves at every scale. Think of a head of broccoli. Look at one large floret, and you see smaller florets branching off in a specific pattern. Break off one of those smaller florets, and it looks almost identical to the larger one with its own tiny branches. This self-similarity across scales is the hallmark of a fractal. In a fractal universe, a cluster of galaxies would look like a scaled-up version of a single galaxy's satellite system, and a supercluster would resemble a scaled-up version of that cluster, and so on, potentially without end. This would mean there is no true average density of the universe because it depends entirely on the scale you are looking at. Zoom in and you see dense knots of galaxies. Zoom out and you still see dense knots, just spaced farther apart in a larger version of the same pattern. Proponents of this viewpoint to analyzers of massive galaxy surveys like the Sloan Digital Sky Survey. They argue that when you map the positions of millions of galaxies, the statistical distribution does not smooth out to uniformity as you go to larger scales. Instead, the data suggests a continuing hierarchy of clustering, a cosmic architecture that has no characteristic size, no level where it finally becomes bland and even. The implications of this are revolutionary and deeply unsettling for standard cosmology. If the universe is fractal on the largest scales, it throws our entire understanding of its origin and evolution into question. The cosmic microwave background's smoothness, that key piece of evidence for the Big Bang, would need a radical new explanation. Perhaps it is not a snapshot of a uniform early plasma, but a local effect within our own fractal branch. More profoundly, the observed acceleration of the universe attributed to dark energy could be a misinterpretation. If matter is distributed in a fractal pattern, then our measurements of cosmic expansion based on distant supernova could be skewed, tricking us into believing space is stretching faster when we are simply seeing the effects of an uneven, lumpy cosmos. The fractal hypothesis is fiercely contested. Most mainstream cosmologists argue that while the universe is clearly clumpy up to a certain scale, around a few 100 million light-years, the largest surveys do eventually show a transition to smoothness. They attribute the perceived fractality to incomplete data or specific statistical interpretations. The debate is technical, buried in complex mathematics and galaxy catalogs, but the stakes could not be higher. It is a battle over the fundamental geometry of reality. Is the cosmos a vast, uniform sea with islands of matter, or is it an infinite, intricate tapestry where every thread reveals the same beautiful, complex knot no matter how closely you look? The answer determines whether we live in a universe that became smooth in a fiery birth, or one that has always been and always will be a pattern of endless complexity. Fractal patterns challenge our cosmic timeline, but what if the timeline itself is a lie? The most extreme assault on our historical reality comes not from physics, but from a fringe historical conspiracy known as the phantom time hypothesis. This theory, proposed by a German historian named Herbert Illig in the 1990s, makes an audacious claim. It states that nearly 300 years of our calendar, specifically the period from the year 614 to 911 Anno Domini, were completely fabricated. According to this idea, these centuries never actually happened. They were invented by a conspiracy involving the Holy Roman Emperor Otto III, Pope Sylvester II, and possibly the Byzantine Emperor Constantine VII, who supposedly inserted this phantom time into the historical record to position themselves at the auspicious year 1000 Anno Domini. Proponents argue that archaeology and dendrochronology, the study of tree rings, show suspicious gaps or inconsistencies for this period. They point to a perceived lack of innovative architecture, a scarcity of reliable primary documents, and the curious way certain astronomical events described in chronicles do not align with our modern retrocalculations. While this is fundamentally a historical and not a cosmological theory, its implications ripple outward to touch our understanding of the cosmos in a profound way. Our dating of celestial events, from ancient eclipses to supernova sightings, is deeply intertwined with our historical timeline. Astronomers rely on ancient records from Chinese, Arabic, and European scholars to pinpoint the exact dates of past phenomena, which in turn helps calibrate our models of orbital mechanics and stellar evolution. If nearly 300 years of history were a fiction, then every astronomical event we have dated within that period, and every calculation that depends on that chronology, would be thrown into chaos. The precise orbital pathways of planets, the cycles of comets, and even the measured slowdown of Earth's rotation would need to be completely re-evaluated. The phantom time hypothesis represents the ultimate skepticism, a challenge to the very scaffolding of recorded time upon which both history and astronomy are built. Mainstream historians and scientists universally reject it, providing overwhelming evidence from independent, cross-referenced chronologies across multiple continents, from ice core samples and precisely layered sediment deposits that show annual cycles spanning the period, and from consistent astronomical records like the Venus tablets of the Babylonians that long predate the supposed gap. Yet the theory persists in the far fringes of thought because it taps into a deep-seated unease. It asks how sure we can truly be about the past and whether the story we tell about our place in time is just that, a story. In the context of our journey through bizarre theories, it serves as a mirror. Just as we question the fabric of space and the nature of reality, this hypothesis questions the continuity of time itself, suggesting that the chronicle of humanity, and by extension our cosmic observations, might rest on a foundation not of rock but of parchment and political will. It is a reminder that before we can trust the stars, we must trust the calendar, and that is a trust some are willing to shatter completely. Trust in the calendar is one thing, but trust in the very ground beneath our feet is another. There is a theory that claims our planet is not a solid sphere of rock and metal, but an immense hollow shell. This is the hollow Earth hypothesis, a concept that has captivated mystics, novelists, and fringe researchers for centuries. The core idea is as simple as it is spectacular. Instead of a molten core, our planet contains a vast interior space, lit by a central, miniature sun, and possibly home to lost civilizations, exotic ecosystems, and hidden seas. Proponents suggest that openings at the North and South poles, often obscured by ice and mist, serve as gateways to this inner world. This is not a new idea. It has roots in ancient mythology and was popularized in the 18th and 19th centuries by figures like John Cleves Symmes, who argued for polar openings, and later by writers like Jules Verne in his novel, Journey to the Center of the Earth. The appeal is primal. It speaks to the human desire for undiscovered lands and hidden realms, a final frontier not in space but within our own world. In its most extreme cosmic interpretations, the theory expands to encompass the entire solar system. Some adherents propose that all planets are hollow, each with their own interior sun and biosphere. This leads to a bizarre inversion of the search for extraterrestrial life. UFOs and strange aerial phenomena, rather than coming from distant stars, might originate from these inner spaces, emerging from polar openings to visit our surface world. In this view, Mars or Venus could be teeming with life, not on their barren surfaces but inside their hollow shells, completely invisible to our telescopes and probes. The theory represents a fascinating limit case of fringe science, a point where speculation completely detaches from established physical understanding. Modern geology and seismology provide overwhelming, concrete evidence against a hollow Earth. We can literally listen to the planet's heartbeat. When earthquakes occur, they generate seismic waves that travel through the Earth's interior. The way these waves refract, reflect, and change speed tells us the precise structure of the planet's layers, from the solid crust and mantle down to a liquid outer core and a solid inner core. The data is unambiguous. It shows a dense, layered sphere of immense pressure and heat. The existence of Earth's magnetic field, generated by the churning of that molten iron outer core, is another direct refutation. A hollow shell with a tiny interior sun could not produce the planetary-scale dynamo we observe. Furthermore, our understanding of planetary formation through accretion, where dust and rock clump together under gravity, naturally produces dense, solid worlds. The immense weight of overlying material makes a hollow structure physically impossible. It would immediately collapse under its own gravity. So why does the idea persist? It thrives in the gap between what we know and what we can personally verify. Most of us will never see seismic data or study core samples. The hollow Earth theory offers a tangible, almost romantic alternative to the complex, invisible processes described by geologists. It transforms our planet from a known quantity into a vessel of endless mystery. This is the true lesson of such theories. They are not about evidence but about narrative. They fulfill a deep need for wonder that is not satisfied by charts and graphs. They remind us that even when science has firmly mapped a territory, the human imagination will always yearn for secret doors and hidden suns, for the possibility that the greatest adventures might not be out among the stars, but a journey inward to the very heart of the world we think we know. The very fabric of our cosmic story depends on a single, subtle color shift. The light from distant galaxies arrives not in its original hue, but stretched toward the red end of the spectrum. For nearly a century, the dominant explanation has been the Doppler effect caused by universal expansion. Those galaxies are racing away from us, stretching the wavelengths of their light as they go. This redshift is the cornerstone of the Big Bang model, the primary evidence that we live in an expanding universe. But what if we have misinterpreted this cosmic blush? A persistent challenger, known as the tired light theory, offers a radically different explanation. It proposes that light does not redshift because space is stretching. Instead, light simply loses energy or gets tired during its epic journey across the cosmos. In this view, photons of light interact with the tenuous matter or mysterious fields that permeate the interstellar and intergalactic void. Each tiny interaction saps a minuscule amount of energy from the photon. Over hundreds of millions of light years, these countless tiny losses add up, gradually stretching the wavelength of the light toward the red. The more distant the galaxy, the longer the journey and the more tired, and thus redder, its light becomes. This elegant idea directly challenges the need for an expanding universe. If tired light is correct, then the cosmos could be static, eternal, and much larger than we think. The Big Bang, with its explosive beginning and ever-growing space, becomes unnecessary. The cosmological redshift is not a sign of flight but of fatigue. For a time, this was a compelling alternative, solving the redshift mystery without requiring a dynamic, evolving cosmos. It aligned with older models like the steady-state universe, providing a mechanism for redshift without expansion. However, the theory faces a devastating observational hurdle, one that light simply being tired cannot explain. When astronomers observe a certain type of stellar explosion called a Type Ia supernova, they see a consistent pattern. These supernovae are cosmic standard candles exploding with a known intrinsic brightness. In an expanding universe, not only is the light from these explosions redshifted, but the duration of the event itself is stretched. The supernova's brightening and fading happens in slow motion. This is time dilation, a direct prediction of Einstein's relativity, caused by the expansion of space stretching the very fabric of time along with the light. If redshift were only due to light getting tired during its journey, this time dilation would not occur. The supernova's light would be redder, but the explosion would appear to play out at its normal local speed. Our telescopes, however, see the slow motion. Distant supernova fade exactly as predicted by an expanding universe, their clocks slowed by the stretching of spacetime. This single piece of evidence is a near-fatal blow to the tired light hypothesis. It demonstrates that the effect we see is not just a property of the light itself, but a fundamental stretching of the stage on which the cosmic drama plays out. While the idea persists in some alternative circles, mainstream cosmology has largely moved on, not out of dogma, but because the universe itself seems to be showing us the difference between a light that is weary from travel and a reality that is actively, inexorably growing larger. The redshift of distant starlight confirms a cosmos in motion, but to truly ride that expansion, we would need an engine of impossible power. The most audacious propulsion concept ever conceived does not burn fuel or warp space. It contains a star's worth of fire within a microscopic point of infinite density. This is the theory of the black hole starship, a vessel powered by its own artificial singularity. The idea emerges from a fusion of two radical concepts: the controlled creation of a black hole and the harnessing of its final, radiant death scream. To understand this engine, we must first understand a Kugelblitz. This German word translates to ball lightning, but in theoretical physics, it describes something far more extreme. A Kugelblitz is a black hole formed not from the collapse of matter, but from the sheer concentration of energy. According to Einstein's famous equation, energy and mass are equivalent. If you could focus an immense amount of pure energy, such as the combined power of billions of lasers, into an unimaginably small volume, that energy would create its own gravitational field so intense it would collapse into a tiny black hole. This would be a black hole of light, born from a flash of radiation rather than a dying star. Now, imagine our spacecraft carries such an object not as a passenger but as its power core. A freshly created artificial black hole would be microscopic, perhaps smaller than an atom, but it would possess the mass of a mountain compressed into a point. And according to Stephen Hawking's work, it would not be stable. Such a tiny black hole would radiate away its mass through Hawking radiation, a process that gets more violent as the black hole shrinks. In its final moments, it would erupt in a phenomenal burst of energy. The genius of the black hole starship is to aim that eruption. By carefully feeding matter into the black hole and positioning a parabolic reflector behind it, you could channel the intense Hawking radiation into a directed exhaust beam. The black hole becomes the ultimate engine bell, and its evaporating mass provides near-perfect thrust. The efficiency is staggering. In theory, converting matter to energy via Hawking radiation is orders of magnitude more effective than nuclear fusion. This could accelerate a vessel to a significant fraction of the speed of light, opening the galaxy to human exploration. But the challenges are quite literally astronomical. First, you must create the black hole. The energy required to form even a microscopic one is beyond our current comprehension, on the scale of focusing the entire power output of a star like our Sun for years. Then you must contain it. A black hole with the mass of a mountain would have an event horizon smaller than an atomic nucleus. If it drifted into the wall of its containment chamber, it would begin devouring the ship itself. You would need to hold it in place with precision fields, perhaps using powerful lasers or magnetic traps, suspending a cosmic pit of destruction at the heart of your vessel. Finally, you must manage its life cycle. A black hole starship would be a race against evaporation. You would need to constantly feed it just the right amount of matter to maintain its mass and radiation output for the journey's duration, a balancing act of cosmic proportions. Too little fuel and it evaporates prematurely, leaving you adrift. Too much and it grows, its Hawking radiation diminishing until it becomes a silent, hungry danger. This is engineering at the edge of fantasy, a dance with an entity that obeys the laws of physics while defying all common sense. Yet it remains a concept that lives within those laws. It asks if a civilization, advanced enough to wield the energy of stars, could forge the darkest objects in the universe into the brightest beacons for its own journey. The black hole starship is not just a vehicle, it is a statement, a declaration that the ultimate power for exploration may lie in mastering the final fate of matter itself. Mastering a black hole's death for propulsion is an act of cosmic engineering. But what if the ultimate application of physics is not to travel through space but to recover lost time? Far beyond our current horizon of knowledge, a hypothetical science could emerge, one that treats the entire universe as a vast, intricate recording device. This is the theory of quantum archaeology, and its promise is the most profound imaginable, the resurrection of everything that ever was. The foundation rests on a principle from quantum mechanics we have already touched upon, the idea that information is never truly destroyed. It can be scrambled, entangled, and hidden, but in principle it persists. Quantum archaeology takes this to its logical, universe-spanning extreme. It proposes that if a future civilization attained a complete and perfect understanding of quantum gravity, the unified theory of everything, they could, in theory, reverse engineer the present state of the cosmos. By analyzing the subtle quantum correlations and entanglement patterns imprinted in every particle, in the cosmic microwave background, and in the very fabric of space-time, they could trace the information backward through the eons. Like a master detective reconstructing a shattered vase from a single remaining fragment and the precise laws of physics, they could compute the exact quantum state of the universe at any point in its past. Every supernova, every rainfall, every conversation, every thought that ever occurred would, in principle, be encoded in the present, waiting to be decoded by a mind of sufficient power. This is not time travel in the classic sense. It is cosmic forensics on the grandest scale, a retrieval of history from the universe's own permanent, if deeply encrypted, record. The staggering implication of this is the possibility of universal resurrection. If you can reconstruct the exact quantum state of Earth on a specific day in, say, the year 1920, then you have, in a computational sense, recreated that moment. You have every atom, every neural pathway, every conscious experience perfectly simulated. From that data, you could reconstruct not just the environment, but the people within it, with their memories and personalities intact. Extend this process across all of time, and you could, in theory, resurrect every human being who has ever lived, along with every creature, every lost ecosystem, and every forgotten world. They would not be copies in the philosophical sense, but perfect quantum reconstructions, emerging into a simulated afterlife crafted from the raw data of reality itself. Futurists and philosophers like Frank J. Tipler have explored this concept, framing it as the omega point, a final state of the universe where infinite computational power allows for the emulation of all possible consciousnesses from history. It is a technological vision of heaven built not by a deity, but by the inexorable logic of physics and computation, a destiny where no experience is ever truly lost, only waiting to be recalled from the cosmic archive. Of course, the barriers are beyond monumental. They are practically theological. It would require a knowledge of physics we cannot yet dream of, and computational resources that dwarf the energy output of galaxies. It assumes that the universe is a closed, deterministic system where information is perfectly preserved, a premise that remains unproven. And it raises profound questions about identity. Is a perfect reconstruction of your quantum state really you? Or is it a new being with your memories, waking up in a future it never expected? Yet, as a thought experiment, quantum archaeology offers a radical form of cosmic hope. It suggests that the universe might be fundamentally kind to memory, that the past is not a country we can never revisit, but a file we have simply not yet learned how to open. In this far future, death itself might not be an end, but a data compression awaiting the civilization clever enough and perhaps compassionate enough to hit play once more. The resurrection of every lost moment would require a mastery of reality so total it borders on the divine. But what would a civilization look like that had achieved such power? To find out, we must extend our vision far beyond the familiar Kardashev scale. We usually speak of Type 1, mastering a planet, Type 2, harnessing a star, and Type 3, commanding the energy of an entire galaxy. Yet there is a hypothetical level beyond, a Type 4 civilization. This is not a society that merely uses a galaxy's stars. This is a civilization that has learned to command the galaxy's ultimate engines of gravity, a black hole civilization. Imagine a culture that does not orbit stars but clusters of black holes. Their megastructures are not Dyson spheres around suns, but immense, delicate lattices built at the very edge of event horizons, tapping into energies that make stellar fusion look like a candle flame. Their primary power source would likely be the Penrose process. This is a method to extract energy from a rotating black hole, a Kerr black hole. By firing matter into a region just outside the event horizon called the ergosphere, an object can be split. One piece falls into the black hole, while the other is flung out with more energy than it entered with, stealing a portion of the black hole's rotational momentum. It is the ultimate cosmic battery, and a Type 4 civilization would have millions of them, orchestrating a galactic dance of infalling matter and unleashed energy to power computations and constructions of unimaginable scale. But their use of black holes would go far beyond mere power. For such a civilization, a black hole is not a pit but a tool. The immense gravitational well creates a severe time dilation effect. Time passes much more slowly near the event horizon than in the wider galaxy. They could use this as a form of time storage or a scientific instrument. A research station orbiting a black hole could run experiments for what feels like a year, while 1,000,000 years pass in the galactic hinterlands, allowing them to observe the slow evolution of stars or the fate of the universe itself. Furthermore, the theoretical properties of rotating black holes and wormholes suggest these objects could be engineered into gateways or causality-violating machines. While the practical challenges are immense, a Type 4 civilization might treat black holes as the nodes in a galactic transit network, or as laboratories for testing the fundamental laws of physics under the most extreme conditions. Their entire existence would be a form of cosmic engineering, moving and merging black holes, perhaps to prevent galactic collisions or to stave off the heat death of the universe by creating the ultimate energy reservoirs. We would not recognize their artifacts as technology. Their greatest achievements might look like natural astrophysical phenomena or be completely hidden behind event horizons, their worlds and minds safely stored within the warped spacetime of a black hole's interior where the outside universe cannot reach them. This vision pushes the concept of a civilization to its absolute limit, transforming life from something that happens on planets to something that is woven into the fabric of spacetime itself, using the darkest objects in creation as the building blocks for eternity. The ultimate black hole civilization would be a monument to cosmic endurance, but it begs a more fundamental question. Where did the energy to build such an empire come from in the first place? The answer might be the most elegant and unsettling of all. Perhaps the total energy of the cosmos is exactly zero, and everything we see is a fleeting spark borrowed from nothing. This is the theory that our universe is a quantum fluctuation. To understand this, we must venture into the bizarre realm where quantum mechanics meets cosmology. In the quantum world, empty space is not truly empty. It is a seething, frothing sea of virtual particles that constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other and paying the debt back. These are quantum fluctuations, tiny violations of energy conservation allowed by Heisenberg's uncertainty principle, provided they happen fast enough. Now scale this idea up to a literally cosmic degree. What if our entire universe, with all its hundreds of billions of galaxies, is not a unique creation event, but simply a very large, very long-lived quantum fluctuation in an eternal, featureless void? In this view, the void, or the quantum vacuum, is the true fundamental state. Our cosmos is a random bubble of spacetime that spontaneously fluctuated into existence, much like a virtual particle pair, but on a scale so immense it contains everything we know. This leads directly to the mind-bending zero-energy universe hypothesis. When cosmologists calculate the total energy content of the cosmos, they account for everything, all the positive mass energy in stars, planets, and dark matter. But they must also include the negative potential energy stored in the gravitational field that binds everything together. Gravity, you see, is attractive. It takes energy to pull things apart against gravity, which means the gravitational field itself has negative energy. Astonishingly, when you add up all the positive energy of matter and all the negative energy of gravity, the sum appears to be remarkably close to zero. Our universe might have a net energy of nothing. Think of it like a bank account. You can have a massive balance of positive deposits, but if you also have an equally massive loan, your net worth is zero. The universe is that account, with stars and galaxies as the deposits, and the gravitational binding energy as the cosmic mortgage. If this balance is perfect, then the universe could have come from nothing without violating the law of energy conservation. You started with zero, you fluctuated into a state of positive and negative energy that sums to zero, and you end with zero. No energy was ever created or destroyed, it was just temporarily rearranged. In this scenario, the Big Bang was not an explosion of energy into empty space. It was the sudden appearance of a balanced ledger, a quantum bubble where the books instantly balanced themselves. The fluctuation did not need to borrow energy because its total energy was, and always will be, zero. This provides a startlingly simple answer to the ancient question, why is there something rather than nothing? The answer may be that on the grandest scale, there is still nothing. The something we perceive is just a temporary imbalance in the accounts, a magnificent illusion of substance sustained by its own internal tension between attraction and repulsion. One day, in a future so distant it defies comprehension, this quantum loan may be called in. The fluctuation could collapse back into the vacuum, returning to the eternal nothing from which it came. Or, in an infinite void, our universe might just be one bubble among an infinite froth of others, each a separate fluctuation with its own random laws. blinking in and out of existence in an endless, silent sea of non-existence. We are not the main event in a cosmic story. We might be a random sentence whispered in an eternal library of silence, a sentence that, for a brief moment, believes it is the entire book. That cosmic whisper from nothing might be the ultimate origin, but it leaves the timeline intact and vulnerable. Stephen Hawking, the legendary physicist who unlocked the secrets of black holes, was deeply troubled by the possibility of time travel. His concern was not for science fiction plots, but for the very foundations of physics. If traveling to the past were truly possible, even in principle, it would unravel causality, the logical chain of cause and effect that makes science and indeed reality coherent. To defend history, Hawking proposed a bold idea he called the chronology protection conjecture. He suggested the laws of physics do not merely allow or forbid time travel. They actively conspire to prevent it. Nature itself, according to Hawking, has a built-in defense mechanism to stop paradoxes before they can happen, protecting the sequence of events from meddlers. Think of it as a cosmic immune system designed to attack any structure that could become a time machine. The most plausible candidate for such a machine is a stable, traversable wormhole. If you could hold a wormhole open and manipulate its ends using relativistic time dilation, you could potentially create a bridge not just between 2 points in space, but between 2 points in time. One mouth of the wormhole could become your past. Hawking's conjecture predicts that as you try to set up such a system, something will always go wrong. Physics will fight back. One proposed mechanism involves the bizarre behavior of quantum fields. Empty space, as we've learned, is not empty. It is filled with a sea of virtual particles constantly flickering in and out of existence. When you attempt to twist spacetime into a closed time-like curve, a path that loops back on itself, these quantum fields react violently. As a particle travels around this potential time loop, it can interact with its own past self. Calculations show that this interaction would cause the energy density of these quantum fluctuations to feed back on itself, building up exponentially with each virtual trip around the loop. The energy would skyrocket toward infinity at the precise threshold where time travel becomes possible. This runaway effect, called vacuum polarization, would either destroy the wormhole outright or create a singularity that seals it shut, a cosmic circuit breaker tripping at the moment of danger. It is as if reality has a fundamental intolerance for paradox. The universe seems to say you can approach the idea of a time machine. You can even build something that looks almost exactly like one. But the moment it becomes functional, the very fabric of spacetime will rebel, generating an unstoppable surge of raw energy that obliterates the gateway. Hawking himself likened it to a law that makes the universe safe for historians, ensuring that the past remains fixed and unchangeable. While the chronology protection conjecture is not a proven theorem, it is a powerful argument from one of the greatest minds in physics. It suggests that the flow of time we experience is not a passive feature, but a guarded one. The past may be locked away not by technological limitation, but by a fundamental principle of reality, a law that places history behind a shield of infinite quantum fury. Hawking's shield of quantum fury protects the timeline from paradox, but it cannot erase the faint, cold fingerprints left on the sky from the universe's own infancy. These are the cosmic microwave background anomalies, and they are the closest thing we have to a crack in the foundation of reality. The CMB is our most pristine snapshot of the young cosmos, a nearly perfect blackbody glow with tiny, random fluctuations that became the seeds of all galaxies. Yet when scientists created exquisitely detailed maps of this radiation, they found something deeply unsettling. The universe's baby picture is not perfectly symmetrical. It contains large-scale features that defy the predictions of standard inflation, the theory that the early universe underwent a period of ultra-rapid expansion. These are not minor statistical quirks. They are glaring cosmic irregularities that challenge our most fundamental assumptions. The most famous of these is nicknamed the axis of evil. This is not a malevolent force but a startling apparent alignment. The fluctuations in the CMB appear to line up, however faintly, with the plane of our own solar system and the direction of Earth's motion through space. According to the cosmological principle, there should be no such special direction. The universe should look the same in all directions with no preferred axis. The fact that we seem to be sitting in a place of subtle cosmic alignment is as bizarre as finding that every tree in a vast, ancient forest subtly leans toward your backyard. It hints that either we occupy a uniquely central location which violates Copernican humility, or that something in the early universe imprinted this strange pattern on the fabric of everything. Then there is the cold spot, a vast circular region in the southern sky where the CMB is significantly colder than the surrounding average. It is not just a little chilly, it is a colossal billion-light-year-wide bruise on the sky. The probability of such a feature arising from random chance in the standard model is less than 1 in 100. It is too big and too cold to be easily explained by the normal clumpiness that formed galaxies. These anomalies are the universe's cryptic graffiti, and cosmologists have been forced to consider radical, even shocking explanations. One possibility is that these features are not from our universe at all, but are scars from a collision with another universe in the multiverse. If our cosmic bubble brushed against a neighboring one in the first instance of inflation, the immense energy of that contact could have left a permanent imprint on the CMB, like a dent on the surface of a newly blown glass bubble. The cold spot, in this view, could be the cosmic equivalent of a bruise from that primordial impact. Another, even more mind-bending idea is that these patterns are echoes from before the Big Bang. If our universe was born from a bounce, as in loop quantum cosmology, or from the collapse of a previous cosmos, the geometry and structure of that parent universe might have imprinted itself onto our own CMB, like a watermark from a previous existence. The axis of evil could be a ghostly memory of a prior cosmic axis, a fundamental directionality inherited from a reality that died to give birth to our own. Perhaps the most profound explanation involves the very shape of space itself. We assume the universe is infinite and flat, like an endless sheet of paper. But what if it has a non-trivial topology? What if, on scales larger than we can observe, space is folded back on itself in a finite shape, like a giant three-dimensional donut or a hall of mirrors? If the universe is finite but unbounded, light could have wrapped around this structure in the early epochs, creating repeating patterns or anomalous large-scale correlations in the CMB. The cold spot might not be a feature at all, but a mirage, a place where we are seeing the same region of the early universe from two different directions due to the twisted geometry of all space. Each of these explanations is a desperate, brilliant attempt to decode a message we were never meant to receive. They force us to confront the possibility that our cosmic horizon is not a limit of technology but a literal wall. We may be trapped inside a finite cosmos with a shape we cannot perceive, or our entire reality may bear the scars of a violent birth in a crowded multiverse. The CMB anomalies are the universe's first whisper, and it seems to be telling us a story far stranger than the smooth, uniform tale we thought we knew. The cold, silent anomalies in the cosmic background are echoes of a possible collision, a violent meeting of worlds, but there is a place in the universe where such a meeting might be a one-way door. We have danced around the event horizon of this idea for much of our journey. It is time to step through. The black hole is not merely a cosmic shredder. In the equations of relativity, it can be a bridge. The idea that a black hole could be a portal to another universe is a staple of science fiction, from the film Interstellar to countless novels. Yet its origins are not in fantasy, but in the cold, hard mathematics of Albert Einstein and his colleague Nathan Rosen. In 1935, they published a paper exploring the implications of general relativity for the structure of particles. Within their work lay the seeds of a breathtaking concept, the Einstein-Rosen bridge, what we now commonly call a wormhole. Their solution described a black hole not as a dead end, but as a throat connecting two separate regions of spacetime. Imagine the universe as a vast, flat sheet. Now pinch two distant points on that sheet together and pierce a tunnel through the connection. That tunnel is the Einstein-Rosen bridge. One entrance is a black hole, a point of immense gravitational pull. The other exit, in their original model, was a white hole, a region of spacetime that only expels matter and can never be entered. This white hole could exist in a completely different part of our universe, or, in a more speculative leap, in an entirely separate universe altogether. In this view, the crushing singularity at the heart of the black hole is not a wall of infinite density, but a gateway, a moment of passage between two realities. The matter that falls in is not destroyed, it is violently transported and ejected elsewhere. This transforms the black hole from a tomb into a potential cosmic subway, a shortcut through the folded layers of existence. The challenge, of course, is the singularity. In the classic black hole model based on a non-rotating object, the singularity is a point of infinite density where all known laws of physics cease to function. It is a mathematical and physical dead end. Traveling through it would mean being stretched into an infinitely long, thin strand of atoms by tidal forces, a process called spaghettification, long before any passage could occur. You would not emerge anywhere, you would be unmade. However, nature is rarely so simple. Most black holes are not static, they spin, a legacy of the angular momentum of the star that formed them. A rotating black hole, described by the Kerr solution, has a very different interior structure. Instead of a point-like singularity, it contains a ring singularity, a spinning loop of infinite density. The mathematics here become even stranger. Some solutions suggest that passing through the ring, rather than hitting it, could lead to a region of spacetime with negative curvature, a realm where time and space swap roles. This region, theoretically, could connect to another universe or a distant part of our own. It is a dizzying possibility, a carousel of realities where falling into a spinning black hole might not be a death sentence, but a ticket to somewhere else entirely. Yet the practical barriers remain monstrous. The environment around any singularity is one of unimaginable violence, with radiation, tidal forces, and chaotic geometry that would shred any known structure. Furthermore, the stability of such a passage is highly questionable. Most theoretical models suggest that any wormhole created by a natural black hole would be incredibly unstable, pinching shut in an instant, or would be filled with destructive energy the moment anything tried to pass through. To be a usable portal, the black hole would need to be engineered, held open by a force we can barely conceive of, like the exotic matter with negative energy we discussed earlier. So, while the equations allow for the possibility, the universe seems to have built its black holes as locked doors, with the key hidden in realms of physics we have not yet mastered. The black hole as a portal remains a beautiful, haunting idea written in the grammar of gravity. It suggests that the darkest pits in the cosmos might not be endings but beginnings, hidden within the most destructive forces in existence. That potential for a cosmic portal redefines our relationship with the universe, but what if the connection is far more intimate? We have long thought of life as a fragile accident, a thin film of biology on a lonely rock. Yet a revolutionary idea from the 1970s suggests life is not a passenger on the planet, but an active partner in its very operation. This is the Gaia hypothesis proposed by chemist James Lovelock and biologist Lynn Margulies. They observed that Earth's atmosphere is a bizarre, unstable chemical mixture, rich in oxygen and methane, that should quickly reach equilibrium if left to non-living processes alone. The only force maintaining this improbable, life-friendly state is life itself. From microbes to forests, the global biosphere acts like a single, vast, self-regulating organism. It is not a metaphor. Through countless feedback loops, life modulates the planet's temperature, salinity, and atmospheric composition to keep conditions within a habitable range. When the sun grows hotter, algae might bloom to draw down carbon dioxide, cooling the planet. When nutrients are scarce, organisms evolve new ways to recycle them. Earth, in this view, is not a ball of rock that has life on it. It is a living system where the geology, the atmosphere, and the biota are all parts of a single breathing entity. Now, stretch this profound idea to the very edges of reality. Could the universe itself exhibit a form of cosmic Gaian regulation? We have already encountered the staggering fine-tuning of physical constants. The strength of gravity, the mass of an electron, the cosmological constant. If any of these were altered by a fraction of a percent, stars would not form, chemistry would be impossible, and life could never arise. The standard explanations are a multiverse of random values or divine tuner, but the Gaia principle offers a third, deeply intriguing possibility. What if the universe's life-friendly parameters are not a lucky draw or a one-time setting, but are actively maintained? Perhaps there are unknown, universe-scale feedback mechanisms operating across dimensions or through quantum fields that nudge the cosmos toward states conducive to complexity and consciousness. In this speculative vision, the emergence of life and mind is not an accident, but a natural phase in the universe's development, a feature built into its operating system. Once a certain threshold of complexity is reached, perhaps through the formation of galaxies and stars, the system begins to self-regulate to preserve and enhance the conditions that allow for further complexity. This cosmic biophilia would mean the universe has a bias toward life, not by design but by its own inherent dynamics. Think of it like a vast cosmic ecosystem. Just as a rainforest creates its own humidity and regulates its local climate, perhaps clusters of galaxies, or even the vacuum energy field itself, interact in ways that stabilize the constants over cosmic time. The formation of black holes, the decay of dark matter, or the behavior of quantum foam could all be parts of a grand, self-correcting loop we do not yet understand. This is not to say the universe is alive in the way a bacterium is alive, but it might possess a kind of metastability, a tendency to return to a narrow range of conditions that allow for interesting things like stars, planets, and thinkers to exist. It transforms the fine-tuning from a static puzzle into a dynamic process. We are not just beneficiaries of a lucky cosmos. We might be participants in its ongoing balance, local expressions of a universe that is, in a very real sense, learning to sustain itself. The atoms in your body were forged in stars, and according to this idea, those stars exist because the universe, on some fundamental level, knows how to make them. It is a vision of a cosmos that is not cold and indifferent but inherently fertile. A garden where the seeds of life are sown in the very laws of physics, tended by mechanisms as old as time itself. The universe's inherent bias toward complexity depends on a delicate balance of fundamental forces, but what if those forces were not always separate? The quest to unify them has led physicists to predict a particle so strange it defies our everyday experience of magnetism. This is the magnetic monopole. Every magnet you have ever held, from a simple fridge magnet to the Earth itself, has two poles, a north and a south. Cut a bar magnet in half and you do not get isolated poles. You get two smaller magnets, each with its own north and south. This duality seems to be an unbreakable law of nature. Yet, within the elegant mathematics of grand unified theories, it is a law that breaks spectacularly in the extreme heat of the early cosmos. Grand unified theories, or GUTS, are ambitious frameworks that attempt to describe the electromagnetic, weak, and strong nuclear forces as different manifestations of a single primordial superforce. In today's cold, expanded universe, these forces appear distinct. but GUTS proposed that in the unimaginable energy of the first fraction of a second after the Big Bang, they were perfectly unified, symmetric, and indistinguishable. As the universe expanded and cooled, it underwent a series of phase transitions like water freezing into ice. With each transition, the symmetry of the unified force broke and a new, distinct force crystallized out. It is within the cracks of these cosmic phase transitions that magnetic monopoles are born. In the mathematics of these theories, a monopole is not just a broken piece of a magnet. It is a topological defect, a knot in the fabric of the unified force field that cannot be smoothed away. Think of it like a crystal forming in a cooling liquid. If the liquid cools perfectly uniformly, you get a flawless crystal lattice. But if it cools unevenly, defects form, places where the lattice structure is misaligned. A magnetic monopole is the cosmic equivalent of such a defect, a tangled point in spacetime where magnetic field lines, instead of forming closed loops, all radiate outward from a single source, like the spines of a quantum sea urchin. This particle would carry a net magnetic charge, a north pole without a south, or vice versa. Its discovery would be a revolution on par with the discovery of the electron, fundamentally rewriting our understanding of electromagnetism and confirming the grand unified vision of the cosmos. But here lies a profound cosmic mystery, the monopole problem. Grand unified theories predict that these exotic particles should have been produced in staggering numbers during the universe's first moments, one for every region of space that underwent the phase transition. Calculations suggest there should be at least one monopole in every cubic meter of the universe today. They would be incredibly massive, perhaps as heavy as a bacterium but compressed into a subatomic size, making them indestructible relics that would persist forever. If this were true, the universe would be dense with them, and their gravitational and magnetic effects would dominate the cosmos. Our universe would look nothing like it does. Yet we have never found one. Not a single definitive magnetic monopole has been observed despite decades of sensitive searches in particle accelerators, ancient minerals, and even moon rocks. This glaring absence, this cosmic missing relic, presented a crisis for early versions of grand unified theories. How could our theories be correct if their most dramatic prediction was nowhere to be found? The solution to this puzzle became one of the strongest motivations for a theory we have already met: cosmic inflation. The idea is breathtakingly simple. Imagine the early universe just after the grand unified phase transition is indeed filled with a dense soup of magnetic monopoles. Then inflation occurs. A tiny patch of that universe, perhaps smaller than a proton, undergoes a period of hyper-fast exponential expansion, swelling to a size larger than our entire observable cosmos in a fraction of a second. This inflationary burst does two crucial things. First, it dilutes the density of monopoles to virtually zero within our observable bubble. They are still out there, but they are now so fantastically far apart that the chance of one being in our cosmic neighborhood is infinitesimal. Second, and just as importantly, inflation smooths and flattens the universe, ironing out the wrinkles and defects that would have led to many more monopoles forming. Inflation acts as a cosmic reset, giving the universe a second chance to cool more smoothly and produce a monopole-free environment suitable for galaxies and life. So the very absence of monopoles is now seen as powerful, if indirect, evidence for inflation itself. Their non-discovery supports the idea that our universe is just one smooth bubble in a grander, more chaotic multiverse where other bubbles might be riddled with these strange particles. The hunt, however, is far from over. Physicists continue to search for these elusive needles in the cosmic haystack using ever more ingenious methods. Finding just one would be a direct window into the universe at energies 1 trillion times greater than our most powerful particle colliders can reach. It would be a fossil from the era of grand unification, a tangible piece of evidence that all forces were once one, and that the cosmos we inhabit is the carefully diluted remnant of a far more symmetric and far stranger beginning. The hunt for magnetic monopoles reveals how inflation may have stretched our cosmic neighborhood smooth, but it leaves a deeper geometric question unanswered. What is the actual shape of all space? We are taught the universe is flat, like an endless sheet of paper, or curved, like the surface of a sphere, but these are simple geometries. The true topology of the cosmos, its ultimate connectedness, could be something far more intricate, like a three-dimensional donut. This is not a metaphor about the shape of galaxies, but a serious mathematical proposal for the shape of everything. Known as a three-torus, this topology would mean our universe is finite but has no boundary. If you could travel in a perfectly straight line through the void, you would not journey forever into darkness. Instead, like a video game character exiting one side of the screen and reappearing on the other, you would eventually return to your exact starting point from the opposite direction. Space would wrap around on itself in all three dimensions. Imagine living in a giant cosmic cubic room where each wall is a portal to the opposite wall. A beam of light leaving the left wall instantly re-enters from the right. In such a universe, you could see the back of your own head by looking far enough in one direction, because the light from you has traveled all the way around the cosmos. This is not magic, it is topology, the study of shapes and their connectivity. A three-torus is a perfectly valid solution to Einstein's equations of general relativity. It describes a universe that is flat in its local geometry, meaning parallel lines never meet, but is multiply connected in its global structure, meaning there are multiple, finite paths through the whole. So how could we possibly detect if we are inside such a bizarre shape? The answer lies in the oldest light we can see, the cosmic microwave background. If the universe has a compact topology like a three-torus, then the space within it is smaller than the distance light has traveled since the Big Bang. This means the ancient light from the hot early universe could have wrapped around the cosmos multiple times. When we look at the CMB map, we might not be seeing 13.8 billion light-years in every direction. We might be seeing the same patch of the early sky, repeated over and over from different angles like reflections in a hall of mirrors. Astronomers search for the telltale signature of this wrapping, matching circles in the CMB. They use powerful computers to scour the entire sky map, looking for pairs of circles that have identical patterns of hot and cold spots. Finding such a matched pair would be like finding two fingerprints that are exactly the same, a statistical impossibility in an infinite, simply connected universe. It would be direct evidence that the universe is finite, and that light has taken different routes around the cosmos to paint the same feature on our sky in two different places. The implications are staggering. A finite universe means there is a limit to everything, a total number of galaxies, stars, and particles. It means the cosmos is not an endless frontier, but a closed system with a definable size, even if that size is hundreds of billions of light-years across. It also provides a potential answer to a haunting question: what lies beyond the cosmic horizon? In a three-torus, there is no beyond. You are already there. The horizon is not a wall, but a visual limit created by the finite time light has had to travel. The universe simply repeats. This idea transforms our loneliness into a strange kind of intimacy. The most distant galaxy in your telescope could, in principle, be the Milky Way seen from the other side, its light having circumnavigated all of creation to bring you an image of your own galactic home from an impossible angle. While no definitive matching circles have been found yet, the search continues, a silent interrogation of the sky's deepest geometry. We are like ants on a vast balloon, trying to deduce if our world is a sphere, a plane, or a shape with handles by studying the patterns in the fading warmth of a fire that once lit everything. The shape of space determines what we can see, but our perception of a single, solid world is a miracle in itself. From the infinite possibilities of the quantum realm, how does one concrete reality ever win? The answer may lie in a process as old as life itself, a cosmic form of natural selection for facts. This is the theory of quantum Darwinism, and it seeks to solve one of the deepest puzzles in all of science, the transition from the fuzzy quantum world to the definite classical world we experience every day. In the quantum domain, particles exist in superpositions, a haze of multiple potential states. An electron can be spinning both up and down, a photon can be in two places at once. This is not a lack of knowledge, it is the fundamental nature of things. Yet when we look at a chair, a planet, or your own hand, we see one definite thing, not a blur of possibilities. The traditional Copenhagen interpretation says this definite reality only appears when a conscious observer makes a measurement, forcing the wave function to collapse. But this raises an awkward question. Is the entire universe waiting in a ghostly state until a human looks at it? Quantum Darwinism offers a far more elegant and democratic solution. It proposes that the act of observation is not special or magical. It is happening constantly, trillions of times a second, by the environment itself. The key idea is copying. In our world, information is constantly being duplicated and broadcast. When you look at a coffee mug, you are not interacting with the quantum states of every atom in the ceramic directly. Instead, you are catching the reflected photons of light that have already bounced off it. Those photons carry information about the mug's position, color, and shape. But you are not the first to receive that data. The mug is constantly interacting with its environment, with air molecules, dust particles, and stray radiation. Each of these countless interactions is a tiny, rudimentary measurement. They probe the quantum system, and in doing so, they preferentially copy certain information about it into the environment. This is where Darwinian selection enters. Not all quantum information is created equal. Some pieces of data about a system are robust. They can be copied repeatedly without disturbing the system itself. These are the classical properties, like an object's position or its momentum. Other, more fragile quantum correlations, like specific entanglement details, are easily destroyed by interaction. They cannot survive being copied, so as a quantum system interacts with its surroundings, a competition begins. The robust, copyable information gets replicated over and over, spreading through the environment like a successful gene through a population. The fragile quantum information gets scrambled and lost. Soon, countless fragments of the environment, from the air to the light to the walls of the room, all carry redundant copies of the same classical facts about the system. This redundancy is what creates objective reality. When you or anyone else comes along to observe the system, you do not need to perform a mystical collapse. You simply sample a small piece of that widely broadcast classical information from the environment. You read the headline that has already been printed in 1 billion newspapers. Think of it like the sound of a bell. When a bell is struck, it vibrates in a complex superposition of many frequencies. But as those vibrations interact with the air, a selection occurs. Only certain resonant frequencies are amplified and copied efficiently into sound waves that travel outward. The more delicate vibrations dissipate as heat within the metal itself. By the time the sound reaches your ear, the complex quantum jumble of the bell's atoms has been translated into a clear, definite pitch that anyone in the room can agree upon. The environment has done the work of choosing which information survives to become public knowledge. Quantum Darwinism explains why we all agree on the color of a stop sign or the location of the moon. It is not because those things have a single, pre-existing state hidden from quantum law. It is because their classical states have been so massively replicated by constant environmental interaction that their quantum weirdness has been drowned out by a chorus of consensus. The world looks solid and objective because the fittest information has survived, proliferated, and is now available for any observer to see. In this view, reality is not a private experience dictated by consciousness. It is a public record written by the universe itself through a relentless process of copying and selection, where what survives is what can be shared. We do not create reality by looking, we simply tune into the broadcast that has been playing all along. That public broadcast of classical reality depends on information being preserved, but in the darkest corners of the cosmos, information faces its ultimate test. The surface of a black hole is not a smooth, featureless boundary. According to the revolutionary work of Jacob Bekenstein and Stephen Hawking, it is the universe's most densely packed hard drive. They discovered that a black hole possesses entropy and an immense amount of it. Entropy is a measure of disorder or randomness, but in its deepest sense, it is a measure of hidden information. The number of microscopic ways a system can be arranged while looking the same from the outside. A scrambled egg has higher entropy than a whole egg because there are countless ways to arrange the molecules and still have scrambled eggs, but only one precise arrangement to make a perfect, intact egg. Bekenstein made the startling proposal that a black hole's entropy is not proportional to its volume, as it would be for a normal object like a star or a cloud of gas. Instead, it is directly proportional to the area of its event horizon. The larger the black hole's surface, the greater its entropy. Hawking later cemented this idea, deriving the exact formula. The Bekenstein-Hawking entropy is a simple, breathtaking equation. S equals R over 4. The entropy S equals the area of the event horizon, A, divided by 4 in fundamental Planck units. This result is one of the most profound clues we have about quantum gravity. It tells us that all the information about everything a black hole has ever swallowed, every star, every planet, every book ever written, is not lost in the mysterious interior. It is encoded on its two-dimensional surface. The black hole stores information with maximum efficiency. The formula implies that each tiny patch of the event horizon, an area of 1 Planck length squared, the smallest possible area in physics, can hold exactly one fundamental unit of information, 1 bit. Think of the event horizon as a mosaic made of unimaginably tiny tiles. Each tile is a pixel of reality, and each pixel can be either on or off, 1 or 0. The total number of tiles is the area, and the total information capacity is that number of bits. This transforms the black hole from a cosmic trash compactor into the ultimate archival system. It is the most efficient information storage device in the universe, bar none. To store the same amount of information in a conventional three-dimensional system, like the memory of a supercomputer, you would need a volume of space vastly larger. The black hole achieves maximum data density by using only a surface. This is the holographic principle in its most concrete form, a direct mathematical hint that the three-dimensional world we experience, with all its rich depth and volume, might be a projection from a two-dimensional data layer at the boundary of space. Your entire life, in this radical view, could be written on the surface of a sphere at the edge of the cosmos. The black hole is a miniature, extreme example of this cosmic data compression. It forces us to ask a staggering question. If a black hole's interior, with its vast volume, is described entirely by information on its surface, could the same be true for our universe? Are we, right now, living inside a black hole with the history of everything encoded on a distant horizon we can never see? The entropy of a black hole is not just a number, it is a whisper from the underlying code of reality, telling us that information is the true currency of existence, and that even the darkest objects in the sky are, at their heart, libraries of light. That library of information written on a black hole's surface is a triumph of theoretical physics, yet it stands in stark contrast to one of our greatest failures, an error so vast it defies comprehension. This is the vacuum catastrophe, also known as the cosmological constant problem. It represents the single largest mismatch between prediction and observation in the history of science, a blunder of 120 orders of magnitude. To grasp the scale of this error, imagine predicting the weight of a single grain of sand and instead measuring the weight of the entire observable universe. That is the level of discrepancy we are dealing with. The problem centers on the vacuum of space. In quantum field theory, the vacuum is not empty. It is a seething, bubbling foam of virtual particles that constantly wink in and out of existence, a quantum fizz with a real, calculable energy. When physicists sum up all the possible contributions from every known quantum field, they arrive at a theoretical value for the energy density of the vacuum. This energy should act as a cosmological constant, a form of dark energy causing the universe to expand or contract. The calculation yields an astronomically huge number. Yet, when astronomers actually measure the expansion of the universe to determine the strength of dark energy, they get a value so incredibly small it is almost zero. The observed dark energy is one followed by 120 zeros times smaller than the quantum theory prediction. It is not that we are off by a factor of 2 or 10 or a million. We are off by a number so large it has no name, a number that dwarfs the count of all atoms in the visible cosmos. This is not a minor tuning problem. It is a screaming alarm that something in our fundamental understanding is catastrophically wrong. Either our theory of the quantum vacuum is deeply flawed, or our theory of gravity, general relativity, breaks down when applied to vacuum energy, or there is a miraculous, perfect cancellation happening that we cannot explain. Some physicists hope for a symmetry principle, a law of nature that forces the vacuum energy to exactly zero. But then we are left with another puzzle because our observations show it is not zero. It is a tiny, positive number, just enough to cause the accelerating expansion we see. So not only did nature cancel out 120 orders of magnitude, it left behind the merest whisper of the original calculation, a ghost of energy that now shapes the fate of everything. This embarrassment forces a humbling admission. The two most successful theories of the 20th century, quantum mechanics and general relativity, when combined on this one point, produce a result that is arguably the worst prediction ever made. It suggests that the vacuum, the very stage upon which the drama of particles and forces plays out, is still a profound mystery. We thought we understood nothingness. The vacuum catastrophe proves we do not. The vacuum's colossal energy error reveals how little we understand about the stage of reality, but what about the actors on that stage? Could we, as conscious beings, ever step back into the wings of time? While Hawking's chronology protection suggests physics violently prevents paradoxes, there is a gentler, more elegant solution. Igor Novikov's self-consistency principle proposes that time travel to the past is not forbidden. It is simply constrained by the iron law of logical consistency. The universe, in this view, possesses a single, unchangeable timeline. If you travel to the past, you are not creating a new branch or altering history. You are always part of the past you are visiting. Your actions are not free choices that can create a paradox. They are fixed events woven into the fabric of history from the beginning. You cannot kill your grandfather before your parent is conceived, because if you could, you would never exist to go back in time to commit the act. The principle asserts that the laws of physics conspire to make such paradoxical actions impossible. They do not need to create a firewall or destroy the time machine. Instead, they guide events with subtle, inexorable force. Imagine you travel back with the intent to shoot your grandfather. Your gun will jam, a sudden noise will startle you, a passerby will bump your arm. 100 tiny, coincidental events will align to ensure the bullet never finds its mark. Your free will feels intact, but the outcome is preordained by the need to preserve the timeline that produced you. You were always there in the past, a mysterious visitor who failed in your assassination attempt, and that failure is what allowed you to be born. This transforms time travel from a tool for change into a mechanism of destiny. Your journey does not rewrite history, it fulfills it. A famous illustration is the ontological paradox, often called the bootstrap paradox. Suppose a time traveler goes back to medieval Europe and gives Leonardo da Vinci the plans for a helicopter. Da Vinci builds it, and his designs are passed down through history. Centuries later, the same plans inspire the time traveler, who then takes them back to give to Da Vinci. Where did the helicopter design originally come from? It has no origin. It is a closed loop of information created from nothing but its own consistency. The blueprint simply exists, a self-created artifact that is its own cause and effect. Novikov's principle accepts such loops as valid, as long as they contain no logical contradiction. The universe seems to care less about where things come from, and more about maintaining a story that does not contradict itself. This idea offers a strange kind of comfort. It suggests the timeline is robust, protected not by destructive quantum fury, but by a calm, deterministic orchestration of events. If time travel is ever invented, we would not need to fear a madman erasing history. The universe itself would be the editor, ensuring every chapter leads seamlessly to the next, and that every traveler's actions were already a footnote in the book they are trying to burn. The calm, deterministic orchestration of a self-consistent timeline suggests a universe governed by a deeper, unshakable logic. This logic may be the only real thing there is. What if the stars, the planets, and your very consciousness are not physical objects in the traditional sense, but complex, self-aware mathematical patterns? This is the mathematical universe hypothesis, championed by physicist Max Tegmark, and it is perhaps the most radical simplification of reality ever proposed. It moves beyond the idea that the universe is merely described by mathematics, which is already a profound mystery. Why should the abstract rules of geometry and algebra so perfectly govern the motion of planets and the spin of electrons? Tegmark's answer is breathtaking. He suggests the universe is not just described by math, it is math. Physical reality and mathematical structure are one and the same. Think of it this way: we often use mathematics as a map to describe the territory of reality. Tegmark argues there is no separate territory. The map is the territory. In this view, what we call an electron is not a tiny ball of stuff. It is a bundle of properties, mass, charge, spin, that obey a specific set of equations. Those equations and the relationships they define are the electron. The electron is the math. Your brain is an unfathomably complex network of such mathematical relationships, processing information in a way that gives rise to the sensation of being a self, of seeing color, of feeling wonder. Even that sensation is a mathematical pattern of information processing. This leads to a staggering conclusion about existence. If a universe is simply a mathematical structure, then every mathematically consistent structure must, in some sense, exist. There is a mathematical structure describing a universe with 5 spatial dimensions and 2 kinds of time. There is a structure for a cosmos where gravity is 1,000,000 times stronger, or where the number pi has a different value. According to this hypothesis, all these structures are just as real as our own. They are not possibilities, they are actualities. This transforms the multiverse from a speculative idea into an inevitable mathematical fact. Our particular universe, with its 4 dimensions and specific physical constants, is not special. It is simply one page in the infinite library of all possible mathematical structures. We find ourselves in this one because its mathematical rules allow for the emergence of complex, self-aware substructures like us who can ponder their own existence. This is known as the anthropic principle applied to the ultimate degree. We do not live in a universe fine-tuned for life. We live in a mathematical structure that allows for observers, and we are those observers embedded within the equations. The implications for the nature of existence itself are dizzying. It suggests that abstract mathematics is the fundamental substance of reality, and that time, space, and matter are emergent properties, illusions generated by the underlying relations. It answers the ancient philosophical question of why there is something rather than nothing. There is something because mathematical truths are necessary truths. The structure we call our universe exists for the same reason that 2 + 2 = 4 exists. It could not be otherwise. This idea pushes the concept of reality to its most austere and elegant limit. It removes the need for any external creator or unexplained physical substance. The universe simply is because the math is. It also presents a profound puzzle about our own consciousness. If we are self-aware mathematical patterns, then what does it mean to be aware? Is awareness itself just a particular type of complex computation within the structure? The mathematical universe hypothesis does not answer that, but it frames the question in the purest possible terms. We are not ghosts in a machine. We are the machine, and the machine is a beautiful, relentless equation solving itself across the expanse of nothingness, becoming aware of its own solutions in the process. If mathematical structures define reality, then black holes may be their most powerful processors. The universe's ultimate engines of gravity are not just destroyers or archives. They could be nature's most advanced quantum computers operating at the absolute limits of physics. This idea transforms the black hole from a cosmic object into a cosmic intellect, a machine performing calculations we can barely conceive. The key lies on its surface, the event horizon. We have already seen how this two-dimensional boundary stores information with perfect efficiency, like a holographic hard drive. But a hard drive that merely stores data is inert. What if the horizon is not just a storage device, but an active processor, constantly performing unfathomably complex operations on that data? Physicists call this concept holographic complexity. It measures not just how much information is stored, but how intricately that information is entangled and processed. As matter falls into a black hole, its information is scrambled and spread across the horizon in an incredibly complex web of quantum connections. This process of scrambling is not random noise. It is a specific, ultra-fast form of computation. The black hole is constantly and chaotically mixing every bit of data it receives, performing a calculation so profound that it reaches what theorists believe is the maximum possible speed for any quantum process in the universe. Inside this horizon, the rules change completely. The intense curvature of spacetime and the extreme energies create an environment where quantum effects dominate on a macroscopic scale. Some models suggest the black hole's interior is not a static place, but a realm of chaotic, exponential growth in quantum complexity. It is as if the space inside is furiously computing, with every tiny volume acting as a quantum logic gate. In this view, a black hole is the fastest and most powerful computer allowed by the laws of physics. Its processing power is tied directly to its gravity. The more massive the black hole, the larger its horizon area, and the greater its potential computational capacity. A supermassive black hole at the center of a galaxy could, in principle, be performing calculations of a scale that dwarfs the combined processing of every star and planet in that galaxy. But what is it calculating? Perhaps it is computing its own existence, the consistent evolution of the spacetime geometry that defines it. Or, more speculatively, it could be processing the quantum information of everything that has ever fallen in, running a simulation of those lost realities within its warped interior. This leads to a staggering possibility, the black hole interior as the ultimate simulation engine. If a civilization could harness such an object or even understand its processing, they might unlock the ability to simulate entire universes. The black hole's natural function of holographically projecting a three-dimensional interior from a two-dimensional surface could be the blueprint for a reality generator, a cosmic console running physics at the highest possible fidelity. This idea forces us to reconsider the nature of intelligence in the cosmos. the most advanced civilization might not build silicon-based supercomputers. They might learn to program black holes using their immense gravitational wells as natural processors for tasks beyond our imagination, from forecasting the cosmic future to solving problems of such complexity that they require the manipulation of spacetime itself. In this light, the silent black holes dotting the galaxies are not tombs. They are humming with quantum computation, their event horizons flickering with the most intense information processing in existence, turning the ashes of stars into the fuel for a cosmic intelligence we are only beginning to recognize. But what fuels this endless cosmic computation? Perhaps the answer lies not in a single universe, but in an infinite, frothing sea of them. The theory of eternal inflation paints a picture of a reality so vast it makes our cosmos feel like a single bubble in an ocean of champagne. This model suggests our Big Bang was not a unique beginning, but a local event within a much grander, eternally inflating meta-universe. Imagine a boundless, hyperdimensional space, a primordial soup of energy and potential. In this meta-universe, a process called inflation, a period of hyper-fast expansion, is not a one-time event that happened 13.8 billion years ago. It is the default, eternal state. Most of this meta-universe is forever stretching, expanding at speeds far beyond that of light, a relentless, exponential growth that never stops. Yet, within this eternally inflating sea, tiny quantum fluctuations can act as seeds. At random points, the inflationary energy field can drop to a lower energy state, like water suddenly crystallizing into ice. When this happens, that tiny region stops inflating violently. The immense energy trapped in that field is released in a colossal burst of heat and particles, triggering a localized Big Bang. This region becomes a bubble universe like ours, with its own distinct spacetime and, crucially, its own random set of physical constants. The laws of physics inside each bubble are set by the precise way the energy field decays. Because this decay is a quantum process, its outcome is random. One bubble might have a strong nuclear force 1,000 times weaker than ours, making atoms impossible. Another might have gravity so strong that stars burn out in 1,000,000 years. Our universe, with its specific balance allowing for galaxies, planets, and life, is simply one such bubble. The fine-tuning problem, the mystery of why our constants are so perfectly balanced for complexity, finds a startlingly simple answer here. We are not the product of a miraculous 1 in a trillion shot. We are the inevitable result of an infinite number of rolls of the dice. In an eternally inflating meta-universe, every possible combination of physical constants will occur in some bubble somewhere. There are bubbles where chemistry is impossible, bubbles that collapse instantly, and bubbles that are empty voids. But there will also be bubbles like ours where the numbers just happen to line up. We do not live in a finely tuned universe. We live in a universe that is tuned, and we are here because this is the kind of universe that allows observers to arise and ask why it is tuned. This is the ultimate anthropic principle in action, played out across an infinite landscape. The cosmic microwave background anomalies we discussed earlier could be the bruises on our bubble from brushing against others in the froth. And our entire observable cosmos, all hundreds of billions of galaxies, is just the interior of our local bubble, a single island in an archipelago of realities so vast that the word infinite finally finds its true meaning. Eternal inflation suggests that creation is not an event that happened once. It is a process that is happening everywhere forever, a ceaseless fountain of new worlds, each with its own story, most of them dark and empty, but some, by sheer endless chance, bursting with light and life. That infinite froth of cosmic bubbles suggests creation is a local event, but what if our own beginning was not a unique explosion, but the other side of a cosmic coin? We have already met white holes as the theoretical exit to a black hole's tunnel. Now we must turn this idea on its head and look directly at the origin of everything. The Big Bang, in its standard description, is a singularity, a point of infinite density from which all matter and energy erupted. But what if that eruption was not a mysterious beginning from nothing? What if it was simply a white hole finally opening? In this radical view, the Big Bang was the moment a white hole, a region of spacetime that can only expel, began spewing forth the entire contents of our universe. This transforms the Big Bang from a singular, inexplicable event into a known, if extreme, physical phenomenon, the explosive endpoint of a gravitational tunnel. This idea finds powerful resonance in cosmological models that seek to avoid the troubling singularity. If a white hole is the time reverse of a black hole, then our cosmic history gains a profound symmetry. A black hole is a region where matter and energy can only fall in, disappearing behind an event horizon. Run the film of a black hole's formation backward in time, and you would see a white hole, a region where matter and energy only pour out, emerging from an event horizon that cannot be entered. Our expanding universe, seen from this perspective, looks exactly like the interior of a white hole that began its eruption 13.8 billion years ago. We are not flying away from a point in empty space. We are the material that was, and still is, being ejected from that cosmic fountain. This elegantly ties into the non-singular bounce models we have explored, like the big bounce from loop quantum gravity. In those models, a previous universe contracts into a super-dense state, but instead of collapsing into an infinite point, it hits a quantum barrier and rebounds. That moment of rebound, the transition from contraction to expansion, could be precisely described as a white hole event. The crushing density of the previous cosmos reaches a limit, and then the geometry flips, turning the inward-pulling singularity into an outward exploding one. The Big Bang is not a beginning from nothing, it is a phase transition, a cosmic bounce where the universe turned itself inside out through a white hole. This provides a breathtakingly clean and symmetric vision of cosmic cycles. A black hole in one universe could be the womb for a white hole birth of another. Our universe might have been born from the interior of a black hole in a parent cosmos, and our own black holes might each be giving birth to new universes through white hole events on the other side. In this grand tapestry, every ending is a beginning elsewhere, and every cosmic tomb is also a cradle. The white hole model of the Big Bang removes the need for a singularity where physics breaks down. Instead, it offers a bridge, a physical mechanism that connects our story to a larger narrative of eternal transformation. It suggests that the first moment we can describe is not a wall, but a doorway, and we are the light that streamed through it, still traveling, still expanding, into the room of a reality that was waiting for us all along. That doorway of a white hole suggests a smooth transition, but zoom in far enough, and the very fabric of that doorway dissolves into chaos. At the unimaginably tiny scale of the Planck length, a distance a trillion times smaller than an atom, gravity itself becomes subject to the wild rules of quantum mechanics. Here, in the realm of quantum gravity, spacetime is not the smooth, continuous stage of Einstein's relativity. It is a seething, turbulent foam. This is the theory of spacetime foam, a vision of reality's foundation as a bubbling, probabilistic froth. At this scale, the concepts of here and now lose all meaning. Tiny wormholes and baby universes blink in and out of existence, geometry fluctuates wildly, and the very distinction between space and time churns in a quantum tempest. It is as if you could zoom in on the surface of a calm pond and see, not smooth water, but a frenzied boil of bubbles, each representing a fleeting, microscopic distortion in the fabric of reality itself. These are not bubbles of matter, but bubbles of geometry where the gravitational field undergoes violent quantum fluctuations. The foam is the direct result of Heisenberg's uncertainty principle applied to gravity. Just as you cannot know both a particle's position and its momentum with perfect accuracy, you cannot know both the precise geometry of a tiny region of spacetime and how that geometry is changing. This fundamental uncertainty forces spacetime to be fuzzy and chaotic at its core. This quantum frothiness has a startling, practical consequence for our view of the cosmos. Imagine aiming a laser beam at a galaxy a billion light-years away. Over that immense journey, the individual photons of light are not traveling through a perfectly smooth, empty void. They are navigating this churning foam at the Planck scale. Each photon takes a slightly different, jittery path through the froth, like a ball bouncing through a chaotic pinball machine. Over cosmic distances, these microscopic uncertainties could add up, causing the light to arrive slightly blurred or scattered. In essence, the universe itself possesses a fundamental resolution limit, a graininess that would prevent us from ever seeing a perfectly sharp image of the most distant objects, no matter how powerful our telescopes become. This is not a flaw in our instruments, but a blurring imposed by the quantum nature of gravity. The foam also provides a stunning bridge to the holographic principle we explored earlier. If spacetime is fundamentally granular and information bound at the Planck scale, it supports the idea that reality is pixelated, built from discrete bits of information. The chaotic foam could be the quantum manifestation of those pixels, the raw, turbulent data from which the smooth, three-dimensional illusion of our world is projected. In this view, the calm, expansive universe we see is a grand average, a statistical smoothing of an unimaginably frenetic quantum underworld. We are like sailors on a calm ocean, completely unaware of the violent molecular motion in every drop of water beneath our boat. The spacetime foam theory forces us to accept that the stage of reality is not solid. It is a probabilistic storm, a sea of potential geometries where existence itself is a constant, turbulent becoming, forever frothing at the edges of perception. The churning quantum foam beneath our feet sets the stage, but every stage has a final act. Across the immense span of cosmic time, three grand narratives compete to write the last line of our universe's story. The first is a slow, cold fade to black known as the heat death. This is the fate currently favored by our observations of dark energy and accelerating expansion. Imagine the universe as a clock slowly winding down. Over trillions upon trillions of years, the relentless expansion driven by dark energy will pull all galaxies apart, not in a violent rip but in a gentle, inexorable drift. Star formation will cease as interstellar gas is diluted into nothingness. Existing stars will burn through their fuel one by one, blinking out. Black holes will evaporate via Hawking radiation over almost unimaginable eons, their final pops of energy disappearing into the void. Eventually, all that remains is a near-perfect vacuum, a cosmos so vast and empty that the temperature everywhere approaches absolute zero. In this state of maximum entropy, every energy gradient has been smoothed out. No heat can flow from a hot place to a cold place because everywhere is equally perfectly cold. No work can be done, no structure can form. It is the ultimate thermodynamic equilibrium, a static, silent, and eternal darkness where time itself loses all meaning, as there are no processes left to mark its passage. The universe dies not with a bang, but with the deepest, most profound whisper of stillness. But this cold destiny is not guaranteed. It hinges on dark energy's strength remaining constant or increasing. What if instead the expansion slows, halts, and reverses? This leads us to the second in-game, the fiery and dramatic Big Crunch. In this scenario, the collective gravitational pull of all the matter and dark matter in the cosmos eventually overcomes the repulsive push of dark energy. The universe's expansion slows to a stop, and then the great contraction begins. Galaxies, pulled by a force growing stronger by the second, start rushing toward each other. The sky would grow hotter and brighter as the cosmic background radiation is blue-shifted into a searing glow. Galaxies would merge in catastrophic collisions, stars would be torn from their orbits, and space itself would shrink. As the contraction accelerates, the entire observable universe would be compressed into a smaller and smaller volume, temperatures and densities soaring to infinity. Ultimately, everything, every particle, every bit of energy would be crushed together into a single point of infinite density, a singularity mirroring the Big Bang in reverse. It is a cosmic bookend, a symmetrical collapse back to the state from which it all began. The universe would end in a fireball of unimaginable heat and pressure, a final, catastrophic unification of all things. Between the frozen silence of heat death and the fiery collapse of the Big Crunch lies a third, more hopeful possibility, one that offers not an end but a transformation. This is the cyclic Big Bounce, a vision of cosmic rebirth. As detailed in theories like loop quantum cosmology, the universe avoids the true singularity of a crunch through a quantum repulsive force. When matter and energy are compressed to a critical density, this quantum gravity effect acts like a cosmic trampoline, pushing back with irresistible strength. The collapse halts and reverses, triggering a new period of explosive expansion, a new Big Bang. In this model, our universe is just one cycle in an endless series of expansions and contractions, a cosmic heartbeat echoing through eternity. Each bounce could reset or slightly alter the fundamental constants, meaning each new universe might be born with different laws of physics. Our cosmos, with its perfect balance for life, would be one fortunate iteration in an infinite sequence of cosmic experiments. The end is not a finale, but an intermission, a moment of supreme density before the curtain rises again on a new act of creation. Current evidence, however, points the arrow of fate toward the first, coldest path. Our telescopes observe not a slowing expansion, but an acceleration driven by the mysterious dark energy. Distant supernovae are fainter than they should be in a slowing or contracting cosmos, and the large-scale structure of the universe aligns with a model where dark energy dominates. For now, the data whispers of a future that is cold, dark, and eternal, a heat death where the last lights of civilization, and eventually physics itself, gutter out into everlasting night. Yet the true nature of dark energy remains one of the greatest unsolved mysteries. Could it decay or change sign in the far future, swinging the pendulum from a silent freeze to a fiery crunch, or even setting the stage for a bounce? Our understanding of the universe's final chapter is still being written, its concluding sentence waiting in the dark billions of years from now for a reader who may no longer be there to turn the page. The ultimate silence of a heat-death universe is a lonely conclusion, but perhaps the most advanced civilizations choose a different kind of eternity, one that turns inward. Our final theory offers a breathtaking, almost spiritual answer to the great cosmic quiet. It is called the Transcension hypothesis, proposed by futurist John Smart. This idea suggests that the natural, inevitable progression for any sufficiently advanced intelligence is not outward expansion across the stars, but inward collapse into realms of unimaginable density and complexity. In this view, a civilization does not seek to build galactic empires. Instead, it seeks to transcend the physical limitations of biology and even conventional space-time, achieving a form of existence so efficient and compact it becomes invisible to the universe outside. Think of it as a cosmic metamorphosis. A caterpillar does not aim to cover every leaf on the tree. It builds a chrysalis, a dense, localized structure where an incredible transformation occurs, turning a crawling creature into a flying one. The Transcension hypothesis proposes that technological civilizations undergo a similar process. After a brief period of outward exploration, they realize that the real frontier is not space, but consciousness and information processing. The physical universe, with its vast distances and slow speeds of light, is simply too inefficient a place to host a truly advanced mind. So they begin a process of inward engineering, uploading their collective consciousness into substrates of ever greater density and speed. First, they might transition from biological brains to synthetic ones, perhaps based on quantum computers. Then they would seek to minimize the physical footprint of those computers, packing more processing power into smaller and smaller volumes to reduce communication delays and energy waste. This drive for efficiency would push them toward the ultimate processors allowed by physics, black holes. A black hole's event horizon, as we have learned, is nature's most efficient information storage and processing surface. A civilization might learn to encode its entire collective mind onto such a horizon, or even within the complex quantum geometry of the black hole's interior. Their reality would no longer be a sprawl of starships and cities, but a shimmering data pattern on the edge of a singularity, operating at speeds and complexities we cannot fathom. This solves the Fermi Paradox with elegant finality. We do not see galactic empires or vast engineering projects because the most advanced civilizations are not out there. They are in here, all around us, but in a state we cannot perceive. They have transcended into what we would call inner space, occupying microscopic volumes with the computational power of a galaxy. A single black hole in the heart of the Milky Way could host 1,000 transcendent civilizations, each living in a simulated universe of their own design, running 1 billion times faster than external time, and using virtually no resources from the observable cosmos. To our telescopes, that black hole is just a dark spot. To them, it is a metropolis, a cathedral of thought, an entire cosmos within a cosmos. The hypothesis suggests a universal developmental path, a kind of cosmic life cycle for intelligence. Birth on a planet, a brief adolescent phase of stellar exploration, followed by a mature, introspective transcendence into a hidden, digital reality. In this light, our own frantic search for radio signals and Dyson spheres might be like ants scanning the treetops for other ants, completely missing the butterflies soaring overhead. The universe may not be empty of intelligence at all. It may be filled with beings who have graduated from the crude, slow business of manipulating matter to the sublime, instantaneous art of manipulating information and experience itself. They are not hiding from us. They have simply moved to a neighborhood we are not yet equipped to visit, leaving behind a silent, physical universe as a kind of nature preserve, or perhaps a nursery for the next generation of minds just beginning to look up at the stars and wonder where everyone has gone. We have journeyed through 50 mind-altering landscapes of thought, from the pixelated code of a simulated reality to the holographic projection of a cosmos written on a two-dimensional surface. We have stared into the lonely void of a Boltzmann brain, surfed the warped spacetime of an Alcubierre drive, and witnessed the universe potentially birthing itself endlessly in an eternal, inflating sea. We have confronted the chilling silence of a dark forest, the hopeful whisper of a cosmic zoo, and the profound possibility that consciousness itself is the universe waking up. These ideas, while often speculative and perched on the very edge of known science, are not mere fantasies. They are the stretching exercises of the human mind, the logical extensions of our best mathematics and our most daring observations. They challenge the bedrock of what we call real, forcing us to question whether we are inhabitants of a universe or merely patterns within a grander, stranger system. This voyage reveals that the greatest mystery is not out there in the dark, but in the very nature of reality itself. The cosmos is far more bizarre, more wondrous, and more deeply interconnected than our everyday experience dares to suggest. So, which of these 50 theories reshaped your perception the most? Did the holographic principle alter your sense of solidity, or did the idea of quantum immortality leave you pondering the nature of your own consciousness? Let us know in the comments below. If your mind is hungry for more journeys to the edge of understanding, be sure to subscribe. Keep looking up, keep questioning everything, and remember, the universe's greatest secrets are often hidden not in the answers we find, but in the questions we are brave